Hello, everyone. Welcome to day 4 of the 2002 IEEE CAS Seasonal School on AI and ML for IC Design and EDA. I'm Andrew Kang from UC San Diego, and also on the Zoom is David Pan from UT Austin, who is the co-organizer of this event. We've had a great 3 days, and today's the 4th and final day of this seasonal school. You can see the agenda for all 4 days here. Today is a day of focus on manufacturability, testing, reliability, and security. We have 3 speakers, Bei Yu, Lisi Wang, and Mohammed Shafique. Today's agenda in particular will have first Bei Yu from CUHK, then Lisi from UC Santa Barbara, and then Mohammed Shafique from NYU Abu Dhabi. Before going on, it's very crucial to thank Leslie Morsek and Lindsay Rogers, who have provided all the logistics and setup. And then we have 4 student co-organizers, Jiaqi Gu, Shaya Kundu, Zhang Wang, and Karen Zhu. This event is sponsored by the IEEE Circuits and Systems Society, as well as by the Telos AI Institute. With that, and without further ado, I'm very happy to turn things over to Jiaqi Gu of UT Austin, who will introduce our first speaker.
Sure, yeah. Thanks very much. Yeah, it is my honor to introduce our first speaker today. And thanks, Professor Bei Yu, for being with us today to give a talk on, actually, the title is a little different. It's a design for manufacturability from layout to chip. And Professor Bei Yu is currently associate professor at the Department of Computer Science and Engineering at the Chinese University of Hong Kong. And he got his PhD degree from ECE UT Austin in 2014. And his current research interests include machine learning with applications in EDA and computer vision. And he was a TPC chair at MLCAD, program committee at DEC, ICCAD, etc., and also the editorial boards of ASM Toll Days and other services. And also, Professor Yu received 9 Best Paper Awards and 6 other Best Paper nominations from prestigious conferences, 6 ICCAD SPD Context winners, awards, and ACM SIGDA Meritorious Service Award and IEEE SIDA Early Career Award. Right, before Professor Yu to starting the talk, if the audience have any question regarding the talk, please type in the Zoom chat box and the speaker will answer them towards the end of the talk or even during the session. And I will give the floor to Professor Yu.
Okay, let me share the screen. Okay, it's really an honor to be here to give a talk about the manufacturability. This is a topic which I have been working on since I joined Professor David Pan's group as a PhD student back in 2010. Okay, so today I will cover some important design stages from layout to chip. So first of all, I guess everyone knows about Moore's law, which was proposed by Intel co-founder Gordon Moore in 1965. And he predicted that the transistor number will increase double every 2.1 years. In the last 5 decades, the whole semiconductor industry works align this law quite well. And this one is actually quite amazing and aggressive law. And many people argue that the Moore's law is dead because nowadays we can see the technology node does not scale down quite well like before. But when we look at the memory, we can still observe very good kind of the scaling, much better than the CPU. So here I draw a picture showing the scaling among the CPU, GPU, memory, FPGA, and flash. Okay, we can see for the flash, we can scale quite well, much better than the CPU. Okay, So here's one concrete example for Apple CPU, and from 2013 Apple A7 with 1 billion transistors, and then in 2016 Apple A10 with 3 billion transistors, with a slightly larger die size, and in recent year 2022 the Apple A6 16 the transistor number is 16 billion transistors. Okay, and another why we can achieve kind of the scaling, main reason is that we can reduce the critical dimension of the patterns. So here is very simple inverter. Inverter contains 2 transistors. Back in 1983, one inverter looks like a big house compared to current size. And along the years, we can see the size of the inverter is smaller and smaller. The benefit of this one is that given the same size of the wafer, we can insert more and more transistors. With more transistors, we can introduce more functionality. We can introduce more memory size. You can imagine that 6 transistors can construct the one bit SRAM cell, and so on and so forth. Okay, but there's no another example is this one, a memory card. Back in 2005, Micro announced the first version of the 128 megabyte, and in 2014, SanDisk announced the first the 128 gigabyte memory card, and now very recent year, and the Micro announced the 1T the memory card. Okay, and that's why someone said the joke that when you want to buy a computer with better the price cost the performance trade-off, you can wait 1 more year. But there's also but there's no free lunch. When we look at the design, and we have to construct the billions of transistors, and we can need to worry about the timing and the connectivities. So the design will be more and more complicated, introducing some manufacturing issues. Okay, and so typically once the design house finishes the design, they will get one GDS file, and this GDS file contains a bunch of the rectangles. Different layers means different meaning, and this GDS file will be shipped to foundry for manufacturing. But when we finish the manufacturing, what we get on the wafer may be very different from, maybe a little bit different from the GDS file description. We can see that there will be some change in terms of shape, for example, rounding on the corner, and also some if we are not well designed, if the manufacturing got some problem, we may have some disappearance or even some big issues. Okay, this right side is an old picture about the lithography system, and essentially using the DUV, we may still be very challenging for the very advanced manufacturing. Nowadays, people already are talking about using EUV, but EUV still have some problems, especially for very advanced technology node. So today I will roughly introduce their flow and the corresponding challenges from the layout to the chip. The layout is generated by design house, okay, and the final chip will be manufactured from the foundry. To make sure we get a good yield, there are lots of things and lots of design stage we need to do. From the top to bottom, I summarize 3 key stages. The first one is this design rule checking. The design rule is provided by the PDK from the foundry, and describing some particular geometrical constraints from the layout side. Once the design has finished the GDS design, they should go through the design rule checking, make sure the GDS can be, the foundry will be okay to make this chip once all the constraints, all the rules are satisfied. Okay, and the next stage will be hotspot detection, where for small design house, they will be very happy once they can pass the design rule checking. But for some very big design house, they worry about the yield very much. If the yield can improve like 1%, and then they can save lots of money. Therefore, they will try their best to analyze the yield. What kind of the design patterns can lead to very good yield, and what kind of design patterns may cause some potential problems. Then that's so-called hotspot detection, to identify some critical patterns in the design, in the layout, and they were trying to avoid this kind of pattern in the future. The last stage will be the mask optimization. This stage typically will be carried out in the foundry to finish the design of the mask. Then the mask will be used in the lithography system. Going through the lithography system, we can really make the pattern on the wafer. Okay, so naturally, my talk today will be split into 3 stages: design rule checking, and then hotspot detection. Last part will be mask optimization. For design rule checking, it's a stage carried out in the design house, and typically they will have a very detailed script describing the rules provided by different foundries, and there will be EDA tool read the rule description and scan the whole layout to check all the whether all the rules are satisfied. There are many rules. Typically, rules include width check, spacing check, enclosure check, and also many others. And we know that the design DRC can increase by 20 to 30% every node. Therefore, the design rule checking will be a very kind of burden to the design house. It's very time consuming. Regarding the DRC research, I have to say there is very little research about the DRC design rule checking. There are several reasons. The first reason is that in academia, we have very little knowledge about the design rules, PDKs. There are some free PDKs available, but those PDKs are not real PDK used in the foundry. And another thing is that for the design rule checking it's a very engineering work. It's very important engineering, but we cannot tolerate any error. So it's really hard for us to say we have very fast checker can achieve 100 times speed up, but it may cause 1% of the probability of error. This is not allowed. So another thing is that we can think about whether we can improve the design rule. Instead of using larger design rule, maybe we can design smarter, smaller design rule. But this kind of work should be done by foundry. Okay, and there's some things academia can do is that we can improve the design rule checking efficiency. Because current single full chip DRC takes hours to days to be finished. Then we can think about whether we can from the design house perspective or EDA vendor perspective, whether we can think about whether we can do some acceleration either multiple CPU acceleration or GPU acceleration. Now, I will talk about GPU acceleration a little bit. Main reason is that this topic is about the originally is about machine learning, and why I talk about GPU acceleration. It's very the reason is that if nowadays people are talking about more and more about the machine learning, then there are lots of the GPU resources available. GPU can help us to do the learning stuff, but since the resource is there, whether our other stage of the EDA tools can take advantage of this kind of resource to also achieve some acceleration. Okay, here I give very simple example, a very simple DRC example. It's about the distance check. Distance check, informal definition is like this: given a layout, a set of the parallel, the polygons objects, and we also are given a design distance rule, which means any two edges must not be closer than a predefined minimal distance. If a pair of edges in the layout violate the distance rule, we call this one as a distance violation. Our task is to report all the distance violations in a minimal time. Okay, so there are lots of rules we can check here. On the right side, I show you some examples. Okay, the problem can be naturally divided into two subproblems. One is horizontal check, another one is vertical check. Okay, so here I show you just example about the horizontal check. Then the distance check is that we are given a set of the horizontal segments, and we try to check whether we find any violation between all the horizontal segments. Okay, and this one is if we try to design a single core CPU algorithm, this thing is very, very simple. You can very quickly write down a bunch of for loop and to do the check one by one. But the problem is that it's really time consuming if we are use very naive implementation on the full chip. Considering that this is just a single rule, we have the thousands of rules to be checked in a very short time. So we have to think about some advanced thing. For example, we can do the DRC checking in a sequential way in a single CPU. We can do it like this way. We have the sweep line search from the X direction, and we check every segment on from left to side, and for each horizontal line, we check whether we have another line in the violation region. This kind of checking can be implemented using very advanced tree structure, kind of efficient, but this one still a sequential way. Another thing is that we can try to do parallel the programming. So for parallel thing, we can take advantage of multiple CPU or GPU to speed up the DRC checking. Okay, so we have two directions, X direction and Y direction. The main idea is that we should decompose the problem by the simple direction for parallelism and leave the complex work to each individual processor for each CPU or GPU. So if we look at the horizontal check, which direction is simpler and which direction is more complicated? Well, we can see that Y direction is a simple direction. We can simply decompose them into a bunch of the horizontal regions. Okay, they have some overlapping, but we can make sure after this kind of decomposition, all the regions can be independent. And for the X direction, because there are a bunch of the overlapping among the segments, it will be very kind of challenging. So that's the typical way we divide decompose the whole chip into the horizontal regions. And for each region, we throw that one into one GPU to finish the parallel checking. Okay, so here is the very preliminary result. We compare with the K-layout. If you are a layout engineer, you must know about the K-layout. K-layout is the only open source the tool. We maybe not the only. Long time ago we have the magic for layout check, but that's the most famous widely used the tool for DRC, LVS, and so on and so forth. Okay, and we do a comparison against the K-layout because K-layout only support multiple GPU conversion, and we have the GPU version. So from here for width check, we can achieve like the a little bit speed up compared to K-layout. But for the enclosing check and space check, we can achieve 60 times speed up and 45 times speed up against the K-layout. Okay, so here's the very simple example what I can imagine about how academia can do something in design rule checking to help the whole EDA tool, the tool chain. The next stage I will talk about the hotspot detection. Okay, it's in the second stage from the layout to the chip. Okay, let me repeat again the motivation about the hotspot detection. Well, even we can, if our design can pass the design rule checking, and we shift the design into the foundry, there may be some error happen on the wafer. So a pattern is called hotspot. Doesn't mean this pattern will cause error for sure. Actually, it has only some probability that one pattern may have error under some special condition of the lithography system. Okay, so we called a pattern is hotspot as those low fidelity patterns. Okay, and we of course can conduct very comprehensive simulation under different conditions to check the PV band, the EPE of all the patterns to make sure to check whether we can detect some EPE variation and which may lead to hotspot. But it's very, very CPU intensive. So this one is a very old picture. This picture I got when I was a PhD student at Professor Pan's group. It's about 40 nanometer, 28 nanometer, and 20 nanometer. And we spent lots of time for the simulation. Now people are talking about 5 nanometer, and for sure the simulation will take longer time. So that's the hierarchy about hotspot detection. So on the top part is sampling, or you can think about this one as a DRC tracking. And the bottom one will be lithography simulation. It's accurate if we get that simulator. Okay, this one is a hierarchical structure, very, very similar to memory hierarchical structure. In memory hierarchical structure, we have several levels like SRAM, DRAM, and hard disk, right? And from top to bottom, we get some trade-off. And here we also have a trade-off. From the top part, it will be very, very fast. On the bottom part for simulation, it will be very slow, but much more accurate. So we argue that hotspot detection in the middle of this kind of hierarchical structure can be a kind of good trade-off between speed and their accuracy. Okay. So that's how, let me show you some classical methodology about hotspot detection. This one is called pattern matching. This kind of methodology was introduced very long time ago. The main idea is that we are given some example about hotspot. These examples can delivered by foundry or delivered by design house when they run some lithography simulation. Okay, and then all the samples will be stored in the library. With this library, we will scan the full chip. Okay, every time we check one clip, we will compare this clip with all the patterns in the library. If we find two patterns are identical, we will say, oh, I got one hotspot. Another, so there are lots of things about the pattern matching methodologies can be applied into this kind of methodology, hotspot detection. And people are also talking about the fuzzy pattern matching, which means even two patterns are not identical exactly. If they are kind of similar, we can also claim we detect one hotspot. For pattern matching kind of methodology, it can be fast. You can imagine this kind of thing is very similar to design rule checking, right? We have a bunch of patterns. We will check using some computational geometry the methodology to check whether two clips are identical or very similar. But it's really hard to detect those unseen patterns. You know, after all, this one is very similar to design rule checking. And another way is called classification-based hotspot detection or machine learning-based hotspot detection. So given this kind of bunch of the hotspot examples, we don't store the hotspot patterns directly. Instead, we try to train a model. We try to learn a model from those samples. And these models can tell us, given a clip, it can tell us whether it's hotspot or not. Okay, then we basically have one oracle. Use this oracle, we scan the full chip layout again, and for every clip we detect, we can query the oracle to see whether it's hotspot or not. It's very classical machine learning classification problem. So you can imagine that many classical methodologies in machine learning field have been applied here, like decision tree, artificial neural network, support vector machine and boosting. Yeah, and the challenging about this hotspot detection is to achieve a good balance between the accuracy and false alarm. If we don't care about the false alarm, we only care about the accuracy, we can simply say the whole chip is hotspot. Then we get 100% accuracy, but we will get a bunch of quite a lot of the false alarm. Okay, and yeah, and about 6 or 7 years ago, people start looking at the deep learning methodology onto hotspot detection. The main motivation is that previously we have to do some feature engineering to get a good feature to represent the layout, and then given the feature vectors, we use some shallow machine learning methodologies. But using deep learning, what we can do is that we combine feature learning and classification in a end-to-end manner. We have a neural network can read the layout directly, and we can go through some convolution layer, pooling layer, and so on and so forth. And finally, we can do some either classification or regression. Okay, and they're using this kind of thing, this kind of end-to-end manner, we can actually learn some pretty good feature, much better feature than previously manual designed features. So here is one very simple visualization. So the first picture is the original layout. Okay, and after 3 layers of convolution, we go to the pooling layer, and we can visualize the feature map on the pooling layer to see, okay, what kind of feature we care about. So we can see from these 4 small pictures, and one is very similar to original one, right? And the 3 others looks like nothing, but when you zoom in, you can see it captures the boundary information about the layout. It tells us what? It tells us for hotspot detection, boundary is very important. I agree with this one, because for the layout, if we know the boundary information, we actually already get the whole picture, all the information about layout. Okay, so I would like to draw your attention about this part, the difference between the layout learning for the layout and learning for other classical traditional computer vision. Well, here is a very kind of the very simple comparison between the imagery hotspot and ImageNet. I mean, on the left side is a picture from the real layout. On the right side is the most famous picture from ImageNet dataset. Okay, so please think about which problem is more challenging or difficult. On the left side, we want to detect whether the layout is hotspot or not. On the right side, we want to detect what kind of what's the picture? Is a cat, a dog, and so on and so forth. Some people will argue that the left side is more challenging because human beings are really hard to get in the label. For example, I actually forgot what's the label of the left side, whether it's hotspot or not, right? We only can get the label after running the simulation or check the log file. Another thing is that to detect whether a pattern is hotspot or not, we should check very large region to get the global information, because one defect may be due to some long distance impact. On the right side, to check whether this is cat or not, we only look at some very local feature. For example, we look at the ear, we look at the eyes, then we know this is cat. Okay, but someone also argue that the left side is easier. Why? Because for example, on the left side for the layout, we only care about the boundary. We have some additional design rule, and we can do the compression without any information loss. Okay, and also on the left side, the input is it's a binary input. Either 0 means it's background, or 1 means it has the layout information. But on the right side, we have to look at the RGB input. The input information will be more complicated. But I would like to argue that these two problems are very different, because for the layout thing, we have some special properties that we have to pay attention. For example, for the same layout, if we zoom in or scale up or scale down of the layout, the label will be changed. But for the right side, if we scale up the picture, it's still a cat. If we rotate the picture, it's still a cat. So we have to think about what kind of the features or what kind of a neural network architecture we have to design to understand the layout better. Okay, so that's a very big problem. I mean, people have tried many years to design different methodologies to help us understand the layout better. So here are some examples, like people trying to design a new representation to represent the layout without information loss. Okay, here are some work quite some years ago, and also there are some simplified architecture for deep learning to learn the layout. So here I show you one example. So if we are given a layout, we split them into a bunch of the grid, and we can when we do the DCT analysis on each grid, we can see that all the patterns, all the information appear on the low frequency component part. And then after analysis, we can throw away some high frequency component, only store a very small portion of the information. But we can argue that using this way, we can still have very little information loss. And by this way, we can transfer the original 2D layout information into a 3D tensor containing the XY location, also the frequency domain information. And then this tensor can be naturally fit into a neural network. Okay. So so here I would like to show another key information about what kind of a thing we should especially pay attention to learn the layout information. You can see in this part, I show you 3 examples about the VIA layout, and on the VIA layout, on the boundary, I also show you the SRAM. Okay, and we can see visually this picture and this picture are very similar, and this picture is very different from these 2 parts, right? If we don't pay special attention, we can imagine that the output feature map after the neural network for these 2 parts will be kind of similar, right? But now we have label whether one picture is hotspot or not. Then we can we know that this one is hotspot, and the bottom picture is also hotspot. But although the top picture is very similar to one hotspot, but it's non-hotspot. Therefore, we should pay special attention, or we should train our model in a special way so that after we get the feature map, we hope the distance between hotspot can be kind of similar, closer, and the distance between hotspot and non-hotspot, even geometrically they are very similar, but distance should be a lot longer. Okay, so there are lots of ways to do this one, and in 2020 we do something like, let me see, we do something about the metric feature learning. So we introduce some special loss function in the neural network. By this way, we can explicitly tell the neural network some patterns, although they are very similar, but you should put some more distance into that one. Okay, and now if you are familiar with contrastive learning, you can see there's some idea about contrastive learning can be applied here to get a better learning, and we can get a gradient for this part. So here is the visualization. Without explicitly learn enlarge the hotspot non-hotspot distance, we can see hotspot will appear in many locations. But if we can introduce a special loss function, and then we can separate hotspot and non-hotspot. Okay, and yeah, I will due to time limit, I will quickly cover one last page about hotspot detection. There are lots of things, lots of architectures we can take advantage of the special chip information. For example, we know the input layout is a binary image, either 0 or 1. Then we can simplify our architecture because the input is just 1 bit. Then we don't need floating value to handle the 1 bit information. Then we can do, but very naturally, we can do some quantization to simplify our architecture. Another thing is that instead of the scan each clip one by one, we can scan the whole chip, make the throughput better. Okay, the last thing I would like to quickly cover is mask optimization. This is a stage carried out in the foundry design. Given the layout from the design house, we assume the design has gone through the design rule checking, it's okay. Gone through the hotspot detection, it's okay. Then we need to design a good mask. This mask will be used in the manufacturing process. Okay, the mask is very important because given the design target, essentially we want to print this kind of the pattern on the wafer. Without OPC, we can design there's identical shape on the wafer, on the mask, but after this manufacturing process, the patterns on the wafer will be very, very different from the design target. We can see that on the we have lots of the shrink here. So essentially, what you get will be very totally different from what you want to design. And then we have to do some additional thing on the mask design. So for example, some region we have some shrinkage on the wafer, then we should enhance that part a little bit. And on the corner, we should have some special the shrink on the mask and so on and so forth. So after the mask, after this kind of special mask going through the manufacturing process, we get a pattern very similar to what we want on the wafer. Okay, and I would like to say the mask optimization is it has some market. The annual revenue is about 100 million US dollar, and there are mainly 4 tools from the 4 major companies: Caliber from Mentor Graphics, Brand tool from ASML, an IC validator from Synopsys, and also the Pegasus tool from Cadence. Yeah, so we can do some approximation about the lethal system using partial coherent system. So the lethal system, if we don't consider source of optimization, if we don't consider TCC, the very, very simple, I should say very, very, very simple version, we can treat this one as a bunch of the convolution. We have the mask M, and we have a bunch of the convolution kernel. And after the convolution, we will get the error image on the wafer, and then we have to mimic the edge behavior to get the final layout, final pattern. Okay, even for this kind of very simple lithograph model, this one is white box. Then we can think about how to optimize the mask. Let me remind you, this is a mask. this this is mask. This is what we want, and then we can think about how we can optimize the M. Then we hope the pattern on the wafer will be very similar to the target. Then we can calculate the gradient step by step. Then we have the gradient for on each pixel about the mask. Then essentially we can do a iterative way to optimize the mask so that the wafer image can be closer and closer to the target. So this methodology is called inverse lithography technique, IRT in short. The IRT, the process is like iteratively, we go through the forward simulation process, and then the backward gradient calculation process, and then forward again, backward again, until we converge. The typical IRT has to split the whole mask into a bunch of the image and then further transfer into the matrix. Then you can imagine, given a full chip layout, the matrix will be super large, and then the calculation, even for a single forward and backward gradient calculation, will be very time consuming. Okay, here's one thing. Another big thing, a big issue about the IoT is about the manufacturability, about the mask, or we have to worry about the MRC mask rule checking, because all the IoT output should be the mask. We still need to make the mask. The mask maker should have some rules. Okay, so we really don't want to have some very special artificial dot spreading on the arbitrary location on the mask. To resolve this thing, another mathematical method is called the level set. So essentially, we have to store a boundary shape, and then we calculate the gradient on the boundary using the implicit representation, but we only focus on the boundary, and then we can gradually update the boundary shape. By this way, we can update the boundary to get a better wafer image. Meanwhile, we will not introduce additional special arbitrary dot on the mask to get better mask manufacturability. There are also some methodology about using machine learning based thing, either shallow learning or the deep learning. For the deep learning, due to time limit, I cannot cover too much detail, but I would like to get a very nice intuition that the image mask optimization is very kind of similar to the semantic segmentation, and then in the semantic segmentation, it's a end-to-end image to image transfer. So for OPC, it's also kind of the image to image transfer, but you may argue why there are so many research on this one, why we don't just simply borrow one model from computer vision field to this problem, then everything's done. But the key problem is that here we have some special model. The big challenge is how we can incorporate the OPC model knowledge, this kind of prior knowledge into the learning scenario. Okay, and another thing is about the throughput. We have to make sure the throughput is good enough. There's one work that trying to compare with caliber only on the VIA layout. We are very happy to see that at least on the result part, the PV band and L2 loss can be better. Runtime can be kind of 4 times faster than caliber. So here's the visualization, how people can achieve the better throughput on the OPC. We will not regularly scan their full chip. We will only focus on some special region where we have some particular pattern. Okay, and I would say that the full chip scale, the OPC is not well studied yet, although there are many research papers. The main reason is that if I ask you what's the most advanced lithography model in the academia, I will tell you it's 48 nanometer, released by IBM in 2013, roughly 10 years ago. Nowadays we are talking about very advanced technology now, but in academia, we only have 48 nanometer. So that's a huge gap from the academia to really push the boundary to go into this special challenge in advanced technology now. Okay, and also there are some scalability issue. When we do this full chip, we have to handle the boundary thing on their mask, and also the manufacturing. We have to worry about the mask rule checking. So due to that time limit, I really have to stop here. So I will be very happy to take any question.
Okay, thanks very much, Bei, for your excellent talk. Right, it's a really great review about several aspects for design for manufacturability. It seems like Jiaqi has asked some question. I don't know, Jiaqi, are you still there?
Yeah, sure.
Let me see. Hotspot detection. This question is how does hotspot detection compare to the object detection in computer vision? Probably some ideas can benefit this field. For example, small object detection, end-to-end object detection without region proposal, and so on and so forth. Yeah, that's a very good question. So also this is a question every researcher in hotspot detection field should think about. I mean, we really should have some prior knowledge when we look at this problem. There are, yeah, you are right. For object detection in computer vision, there are kind of the one stage or two stage thing and some special methodologies. The good news is that many of the methodologies in computer vision can be applied in hotspot detection, but one special thing for hotspot detection is that to check whether one pattern is hotspot or not, we have to, wait, where's the picture? Yeah, here. We have to look at the very large region. This is very different from the traditional object detection. Because for object detection, we look at every region and we do the classification for the within this region, right? So that's the main thing. For others, yeah, there should have some others. Oh, right. The input is a binarized image, not the RGB. Okay. Another question I see from the chat box is that do you vision the machine learning model for mask hotspot spots can be deeply integrated into the physical design flow? For example, hotspot aware detail routing with machine learning hotspot model. I believe so. Also, although I'm not sure whether it will be very practical, because nowadays you can think about the physical design. People are already trying to integrate many things like the congestion, like detail routing, DRC variation, like timing, heat, all these kind of things into the physical design engine, right? and in our engine, we already have lots of things to worry about. For the hotspot detection, yeah, of course, there was several works talking about lithography aware detail routing. I believe both Professor Andrew Kahn's group and Professor David Pan's group had done some work there. So of course we can do this way. If you ask me whether I will do this one now, probably no, because in physical design we should worry about more important thing like timing. Timing is always the most important thing. And for the manufacturability, even there's some hotspot, we still have one stage to save the manufacturability, which is what? OPC. We can worry about advanced OPC methodology, not edge shift kind of OPC. We should think about IoT kind of OPC to improve the process window. So that's my short answer to this question. Another question is that it's trustable, or we always want to turn the design on the checker up to one issue in practice, for example.
11.
Okay.
The dial goes from 1 to 10, but it's an old joke from a movie, I think, that you turn the dial up to 11 because
Okay.
you want the absolute best accuracy because it's your tape out. So,
Okay.
so is this a problem with the migration of machine learning or AI into these kinds of final verification flows?
That's a very good question. I mean, every researcher in EDA field, when they use machine learning methodology, they have to answer this question, because for machine learning, we cannot guarantee 100% accuracy. If we get one error, then what will happen, right? Right, and then that's why, as I show in the very first picture of this part for the design rule checking, I said there's nearly no, or only one work applying machine learning, deep learning to the design rule checking, but I'm not sure whether it's really useful, because in the design rule checking we cannot tolerate any error. But in hotspot detection, because we're trying to improve the yield, and we're just trying to reduce the low fidelity pattern, so some error can be okay. For mask optimization, I really trust the machine learning model, because for mask optimization, machine learning can be integrated with the traditional methodology. For example, we take the IoT and level set method, for example. So they are iterative methodology, and the performance really depends on the initial solution. Okay, so if we don't have machine learning thing, we have to generate a random initial solution. And more importantly, the model is non-convex. And then if we start from not good initial solution, then we will be stuck at very bad output of an OPC process. So machine learning kind of thing can save lots of the iteration number in OPC. We can save lots of really runtime. That has been verified in many research papers. So a short answer to Professor Kahn's question, for hotspot detection and the mask optimization, I really believe the machine learning methodology. For design rule checking, probably no.
Thank you.
Hi, thanks, Bei, again. I think time is up for your talk, and thanks again, right? Please, if you have more questions, right, you may type the questions here, and Bei, you can stay a little bit, I guess. It's very late, I know, you're in
Sure, I can stay here for a while. Yeah.
A little bit, but anyway, we have the next speaker, Professor Wang here as well now. So Judge, you can help introduce our next speaker. Can you pour?
Yeah, sure. Let me share the screen. Okay. Right now, our next speaker is Professor Wang, and I'm glad to have you with us today to give us the talk on machine learning for testing and yield. Professor Wang is currently a professor of the EC department at UC Santa Barbara. He received his PhD in 1996 from UT Austin, and was previously with Motorola PowerPC Design Center. He has worked on machine learning for design and test flow before, and in recent years, his research focused on building a virtual assistant for semiconductor test data and analytics. He received 9 Best and 2 Honorable Mention Paper awards from major conferences, for example, ITC, VTS, VSI, DET. He is also the recipient of the 2010 Techno Excellence Award from Semiconductor Research Corporation, SRC, and the recipient of 2017 IEEE TTTC Bob Batch Innovation Award. He's an IEEE Fellow and was the General Chair of the ITC. He will also be the General Chair of ITC in 2023. And in 2017, he participated in the founding the first ITC Asia conference and served as its General Co-Chair. So before the talk, I also want to mention some logistics. The audience can type any questions for our speakers in the Zoom chat box, so our speaker can answer those questions toward the end of the talk. So let's welcome Professor Wang to start the talk, and the floor is yours, Professor Wang.
Thank you very much for the introduction. Can you hear me okay? Can you hear me okay? My voice is okay?
Yeah, it's okay.
Okay, thank you. Yeah, sometimes my my microphone may be it's directional, so I have to place my mouse to yeah. So let me share. So can you see my screen okay now?
Yeah, it looks good.
Oh, okay, good. Okay, thank you. Okay, thank you very much for letting me share my research experience with you today. And I think in this talk, I will discuss my experience in the domain of semiconductor test data analytics. So before I start, please keep in mind that the perspective I'm in all my presentation today is strictly from the viewpoint of test data analytics. And I want to emphasize that I'm not talking about in the of machine learning in the context of achieving full automations or any like AlphaGo like optimization context. So maybe here, you know, is a little bit switch of context from all the previous talks you heard in this forum. So I would like to start by telling you a success story back in 2014. So the story goes like this. At the time, we were working very closely with Freescale Semiconductors. And my friend presented me with this challenging problems. And the problem was on an automotive SoC product line. So what happened is that the yield on that product line fluctuated over time. And of course, this illustration is not a real yield curve, which is confidential. And the point is that people had to try to solve the problem for some time, but was unsuccessful. So they actually went through one design revision, multiple test revision, and even some foundry process adjustment without any success. And before the problem given to us. So we were given all the test data and asked if our quote unquote machine learning expertise could help them find a resolution of the problems. So to give you a little bit about background of that problem is that in testing, the first stage of testing, we call it E-test stage, or sometimes called it class pro, sometimes called it parametric testing. So what happened is that in that testing stage, you measure unprocessed parameter on K site for each wafer. For example, N can be 400 and K can be 8. And they're used as an indicator to the health of the wafer, a particular wafer, because this is done on every wafer. And the next stage is called wafer probe. And this is where parts are decided to be good and bad. For example, from wafer probe, we can collect statistics like this, showing wafer to wafer failing statistics organized by this so-called test bin. For example, this chart shows you bin 26, 25, 28. And the problem is to try to correlate a type of failing mode to some e-test parameter if we can. So it is important to note that any correlation we found require also expert approval. It's not like we said it's correlation and they will agree. And if you look at the whole problem, it's essentially a search problem. So these were some of the best results from our initial involvement. And these results were not convincing enough to initiate a silicon experiment, or in other words, asking the foundry to change their recipe. And in this case, the foundry is another company. So roughly like about 4 weeks after we get involved, and we had a breakthrough. The breakthrough is that when we actually narrow down to a particular failing mode, and then we can call it X4. And we were able to find a good correlation between X4 and one of the parameters, we call it PP1 here. So in the next several weeks, we continue to find ways to strengthen the correlation finding. And the reason is because we have to convince the product team that we had found something real. So one way to explore this for this improvement is to explore this so-called temporal effect. For example, you can see here, if we could unmask the temporal effect, we could find better results. And in other words, if you look at there's a two correlation trend showing here, and they have a shift because of the process variation across from wafer to wafer. So eventually, we found 5 relevant process parameters, which result in 2 separate process recipe change, and agreed by the foundry. And the foundry had done 3 experiments, with 1 experiment including both changes. And the results showed that significant yield improvement and reductions of the yield fluctuation. And as seen in this chart, each change contributes to their own yield improvements. And when we implement both change, and that got us the best results. And it is important to know that before the product team and the foundry accepted our recommendation, we had to show them a lot of evidence. One of them is to convince them that our suggested change would not cause another yield problems. And in other words, we have to tell them that the risk of our suggested change, what does that mean? And this means we need to show them that other failure modes do not correlate to the process parameter we're suggesting, like change on the PP1. The method is a little bit complicated, but the high-level idea is that we could measure the complexity of establishing a correlation as the risk. Let me show you an example. For example, we evaluated the risk of changing the parameter PP1, and we found that the fail mode being 31st had the highest risk in this chart. Then that's not enough, because then we go back and look at these plots, and then we can show this plot and show both plots to the team, and then convince them that, say, look, a bin 31 failing mode had no obvious correlation to PP1. So in this case, we had to show them no correlation. Well, the story was certainly very exciting at the time for us, because after all, it was the first time we saw our work actually made a huge difference on company's bottom line. But the excitement we had faded away not too long afterward. Well, in the next few months after we published the paper, we were pondering on this question: where was the machine learning in our work? When we thought about our work, we could see that what we did was essentially a process where we pick a failure mode and we search for a correlation. Then we pick another failure mode and we search for correlation. And the process continued for quite some time until we hit the jackpot. And in the data given to us, there were predefined failure modes already there, and searching on them was not successful. And our success really started by finding the particular X4 failure mode by ourselves and manually. And this, of course, depends on somewhat know-how intuitions. And in the process, what we really need was a way to tell us there's no correlations, so that we could get out of each particular correlation effort in all those boxes quickly and to improve the efficiency of the analytic process. And when we look at such a process, it seems that we did not apply machine learning in a regular way, right? And instead, we use machine learning to show there's no correlations. And there was no way machine learning could pick the failure mode X4 because the data just did not define X4 as a separate failure mode. So in other words, if you think about these pictures, and if we consider all possible answers that can be derived from the given data sets, our answers actually lying outside. And we need a tool to tell us there's no answer with this data set. And we need a person to point out that to try here. So in this view, a pure data-driven approach will not work. And we certainly need expert inputs. So after the 2014 experience, and we started to wonder, was this no regular or no typical machine learning situation unique to that particular problem, the yield problems, or it is common to other contexts we had encountered before? Then we thought about the work we did several years earlier in the context of so-called design silicon timing correlations. Well, for the same company, by the way, the specific problem was that we observed on silicon chips some paths were faster than the STA prediction, the static timing analyzer, and some paths were slower. And the interesting part is that those paths were actually kind of similar paths, and there was no obvious reason why this happened. So our test was to find out what caused those similar paths to behave differently. The analytic methodology, started by defining a set of features to describe those paths. Then we asked what combination of those features could explain the unexpected silicon behavior. Well, speaking about feature, here's some of the examples, some illustration to give you an idea how you can derive those features. Those path features hypothesize the source of uncertainty on the path. In our work, for example, we could consider from the layout and the design schematics, we can consider a feature that were cell-based, what kind of cell we use and what kind of property. We could consider a feature that originated from transistors, for example, transistor strengths, and we can certainly consider feature that related to the interconnect. And at the end, we uncover an interesting finding we present as a tree models. The tree models say that when there are greater than 14 single via between metal layer 4 and 5 on a path, and greater than 70 double via between metal layer 5 and 6, then it is likely to be a slow path. And we can actually visualize this model in this color plot, where the paths classified as slow are highlighted in orange color. And later, we actually validate this finding with the process team. And they told us that, yes, there were indeed an issue they knew on the metal layer 5. And again, in this work, if we think about it, if we did not include that particular via feature, we will never reach the answer. So you can imagine that when in that work, the timing correlation work, when we started, we could start with we actually started with a simple set of features, and we could easily get. But we need a tool to tell us there's no answer there, so that we don't get stuck there, and we know to explore other options. And of course, in the process, we still need the expert inputs. And then we thought about a related problem that is about post-silicon speed path analysis. So in this example, we have the data to tell us which passes are the speed limiting paths on a high-performance microprocessor. And this is with another company. And for example, you can see in this chart, there are 4 paths limiting the speed, the top 4 paths. The y-axis shows their predicted timing slide by the static timing analyzer. And we saw that STA considered them as non-critical paths because these 4 dots are above the criticality threshold and show as a horizontal dashed line here. And our learning is to explain why those paths are speed limiters. Again, to start, we need to prepare a data set and data-related features to encode every path into a feature vector, such as F1 to Fn. And this encoding will provide us with a data set look like this. But this data set is different from the previous problem because on this data set, we have only one positive sample because we analyze every speed path individually. And we have many other negative samples as non-speed paths. And the learning is to discover a rule to explain the positive samples. And this learning is more challenging because of so few positive samples. So in that ITC 2010 work, speed path analysis, we did find some interesting explanation for those speed paths. And here's some of the results, snapshot of the result. From the rule we found, we saw the feature CMAC were involved in several times. And later we confirmed that the CMAC was really related to the problem. And once again, the success of the story depends on we knowing that to use the CMAC features. Then we realized that even for the work we did in the functional verifications, it was very kind of similar to the speed path analysis work. And in functional verification, we are working with an RTO models. And our goal is trying to find a functional test to hit the coverage point, say point A, which either had few coverage or had no coverage at all so far. And we desire to hit this coverage point many more times. And our feature in this case is a set of so-called microarchitecture signal that we know we can control from the test templates. Then we ask the questions, what combination of those microarchitecture signal can hit the coverage point A by activating them? So the context is similar to other we talked about earlier because we need to have the right set of the signal in order to get to the answer. And the learning is also with very few positive sample, and sometimes can even have no positive sample, none. To facilitate search, we need a tool to tell us there's no answer for a given data set we constructed. So that's not it. In testing, one of the popular contexts is to learn a model to predict so-called future fail. A future fail means that the part passed all the current tests, but still fail in some future testing. For example, a customer can perform their own system test and can observe a failing part at their site. So in the test community, a common approach to deal with this problem is to develop a so-called outlier model to screen a known future fail. For example, this picture shows a burning fail, and every dot on this picture is a part. And test A1 and test A2 are tests done at the wafer probe. These are before the burning. And the red dot is known future fail or known burning fail, show like outlier on this chart. So the failure analysis results show on the bottom right confirm the fail. You can see there's some kind of impurity there on the pictures. So, however, this example show you that in some situation, predicting future fail with an outlier model is unlikely. So in this case, we found that test T that screen many fail only after the burning. However, when we look at the test T before the burning, only 2 parts marginally failed the test. And in other words, the burning actually, the process did change the intrinsic characteristic of the chips, and so that it will change the value of the T on many, many parts. So that tells us that without the burning stress, it's very difficult to screen out those fail with the particular test. And in other words, we have to introduce new tests rather than use the existing tests. So in order to know that we have to use burning in that predicting future fail story, we need a way also to say that there's no outlier model, so that we for the test data we have. So, and we can consider that as a reverse outlier question. In the reverse question, we're given a part which is known future fail, and our task is to search an outlier model to project the given part as an outlier. For example, in this part, the red dot is a part we're interested in projecting as an outlier, and this particular model is not good, is not acceptable, because with a different scale, we can see the part does not look like an outlier anymore. So we can think about the problem as a search, like the branch and bound process. And in the search process, we need an efficient way to determine there's no outlier in every one the branch, so that if overall there's no outlier, we can determine there's no outlier for the entire for the data set in our search, and therefore we could resort to other means such as creating new tests. So let's consider why it is cumbersome for the traditional outlier analysis to decide there's no outlier. Well, in outlier analysis, we start with a set of samples. An outlier method is selected, which calculates an outlier score for every sample. The score are used to decide an outlier rank. A threshold is selected to separate the inlier from outlier. So in outlier analysis, the choice of the sample is subjective. The choice of the threshold can be subjective, and both make it difficult to say there's no outlier. And so if you're interested in this problem, we had a practical solution, which we published in BTS 2016. And if you're interested, you can look at that kind of approach. So anyway, the main point here, the main message I want to convey is that once again, if we look at even that problem, this is what we need, the same picture applied. So after we kind of review all this work we have done in the past, in about 2017 and 2018, and we start doing a lot of reflections on all this past work. So for many years, then my group had tried to apply machine learning in the in a data analytic context based on data originated from design, manufacturing, and test. For example, in the design, and where we analyze data to improve functional verification, to predict performance, or to improve simulations. In the manufacturing, we work on problems such as optical inspection, defectivity analysis, or monitoring the manufacturing equipment. And in the test, we of course work on applications such as adaptive tests, yield optimization, outlier analysis, and diagnosis and debug. So overall, if we look at the almost all the application contexts, either we're trying to learn a model to predict something, or we learn a model to explain something, or both. Most of the time to predict, but won't accept the model unless we can explain it. So starting from 2018, then about 5 years ago, we started to focus on, based on all this experience, we started to focus on asking these questions like these. So we're really wondering, what is so special about machine learning in our domain, but in the test data analytic domains? And is there a fundamental gap between machine learning and machine learning in our domains? Or we can just briefly say, domain-specific machine learning, or DSML. And also another fundamental question we're wondering is that how do we leverage the growing state-of-the-art machine learning technology? So we were interested in understanding what we call a DSML gaps. So on one end, we have this machine learning AI technology available from the machine learning community. And many of technology already been packaged and enable us to achieve local AI implementations. On the other end, we have our domain-specific problem I just mentioned, and in the data analytic context. And we want to know if there's a fundamental gap to connect the two, or is our DSML just about pick and choose a technology and apply on the domain-specific data. So next, I will summarize observation from our reflections with high-level pictures. So for almost all the problems we work on, it seems that the analytic tasks are performed in an iterative fashions. There is data which is derived from the process. The process essentially is our data generator, and the process whatever we try to improve as well. Both data and process can evolve over time. So putting another pictures here as an iterative process. So it can be anticipated that some aspect of the future data deep prompt after the improved targets cannot be predicted by applying machine learning on the current data deep. And in fact, this unpredictability can actually be the value we're looking for from our iterative learning process. And we can think about the picture I just talked about from a data view, a data set point of view. From one iteration to the next, our DSML might be used to enrich the data set in two directions. We want to attain the feature unknown before, or we want to attain the sample not seen before. So to summarize that, what we observe, we can use a postulate to summarize. So this postulate reads like this. For domain-specific machine learning problem in our domain involving a data generator G, the goal of the learning based on dataset D given through G is to modify G so that we obtain a new dataset D prompt, where D prompt contains a new information that is unknown before. So if that is the situation, then in our work in 2017, if the DSML we deal with is some sort of unpredictability, that brings us to the concept so-called no-free lunch. So basically, if we consider the hardness of the machine learning problems, on one end, we have the so-called efficiently learnable. On the other end of the spectrum, we know the ceiling is called no-free lunch. And so we kind of observe that the problem we're dealing with somehow stay close to no-free lunch, and we call it local no-free lunch. And if you're interested, you can see that paper. And the situation really happened is that when the data at hand is not representative for the future, and in that case, there's no learning method is universally better than other. Therefore, it's a no-free lunch situations. So, so the important idea of local no-free lunch is that because especially important when we're dealing with the content in post-silicon productions. In the production, there are usually three stages: the initial yield learning stage, the ramp-up stage, and the mass production stage. The learning required, usually is most demanding in the first two stages before the mass productions. And for example, that's when we want to predict what happened in the mass production stage. And local no-free lunch is almost inherent in such a learning context setups. And again, you can see the paper to talk about those concepts. So in summary, what we're talking about here, what is the difference between what we observe the difference between machine learning on our view of our domain-specific machine learning? Well, to think about machine learning, we can simplify into three major components in the machine learning setup. We have a sample generator we talk about that will produce a training set. To learn, we come up with a hypothesis space assumption H, comprising many or sometimes infinite hypotheses. In the middle is our learning algorithm that try to find the best hypothesis for the given data set. In machine learning, the assumption is that the sample generator G is stable. We usually assume a fixed hypothesis space, and this enables us to formulate the learning problem, solving an optimization problem. In the DSML we talk about, the G is actually the one to be improved, and our assumption is actually the one to be learned. So in other words, we are searching for a hypothesis that can be validated by the data. So if we have to compare DSML, machine learning and versus domain-specific machine learning in our domain, we could say that the machine learning focus on optimization, our DSML focus on data understanding, the machine learning focus on making the predictions, our DSML focus on making the suggestions. The machine learning is powered by big data, and our DSML is powered by domain knowledge. And overall, machine learning assumes a world of free lunch, and our domain-specific machine learning can enter a world of no free lunch. So next, I would like to a little bit sidetrack, spend a few minutes to mention our simple view of machine learning from the perspective of our specific domain-specific machine learning. So in an intuitive way, we can think about machine learning as playing a guessing game. First, let's assume that there's this dark entity whose insights we cannot see, but we desire to model or to understand it. Say this dark entity has its own mind, and this mind assert a true answer to begin with. Say the answer is simple function f equal to y, x, y, z. The learner job is to guess what is the correct answer in the dark entity mind. And some data revealed by the dark entity, quote unquote, is, or you can call it observable evidence, revealed to the learner. And in such a view, I think the fundamental question we can ask is that does learner have the hope to win or to guess correctly? Well, to start, the learner can begin by assuming a hypothesis space. For simplicity, let's say the space only has 5 hypotheses. Then the learner used the data sample to filter out hypotheses that do not fit the data sample. For example, maybe with the initial evidence, H1 does not fit, hence we know to eliminate H1. Then with more evidence provided, maybe we can eliminate H2, 4, and 5. And at the end, H3 is not eliminated, left, and therefore we say the answer is H3. So of course, in practice, the hypothesis space is not that simple, can be a continuous space with a finite hypothesis, but the basic idea remains the same, that we are filtering out hypotheses that do not fit the data sample. Now suppose we have a hypothesis space, and now suppose we have seen some data sample, a portion of the space is filtered out, and in the space, there are still many hypotheses that all of them can fit the data samples. And the question is that which one will pick as our answer? Well, a common practice is to follow this so-called open razor principle, that we will pick the simplest hypothesis as our answer. In other words, learning can be seen as essentially a data fitting or filtering process, plus the open razor based optimization. And if we translate this view into practice, and that's why we probably observe in many times what learning is due can be captured by a minimization problem of these two terms. One is the fitting error, the other is model complexity. And the fitting error is detected by the sample. The model complexity, usually we also call them a regularization term. And the alpha here is to balance the trade-off between the two, is called regularization constant. So now if we ask ourselves, if that is the essence of what the machine learning is doing, what guarantee it can provide? Well, to be honest, I don't have an answer for that, because it is a very difficult question to answer precisely. Because in essence, it is asking what is the true meaning of Occam's razor. But I will give you my thinking in the next slides. Suppose we have a huge hypothesis space, and suppose the space is partitioned into subregions based on their complexity level. Suppose this level is, we can say, is 1 to 1,000, and assume the true answer is at complexity level hundreds. And in the learning process, after we see some initial data, Our simplest model has complexity 1, so we set a 1. After seeing more data, the data forced us to increase our model complexity to level 5. And as more data coming, eventually we are forced to incrementally increase our model complexity and reach the true answer at 100. By following OpenRazor, as soon as the data becomes sufficient, we will reach the true answer. And this path is driven by the data. And suppose we don't follow this path, we follow our own path, follow another path, and that path inevitably will include some of our subjective guesses. And because the space is so huge, any of our subjective guesses will more or less look like a random guess. And the consequence is that even when the data is sufficient, our subjective guesses may prevent us from seeing the truth. And consequently, we need more data to remove our own subjectivity, which in a sense is less effective. So what it guarantees of following the OpenRazor is that we don't get lost in the huge hypothesis space due to our own unjustified subjectivity. But now ask this question, if the space does not have the answer to begin with, then in this case, if the OpenRazor as the first principle will not save us. And more importantly, if we try too much optimization, excuse me, we may even get trapped. So in summary, I think when we talk about our learning problem, domain-specific learning problem in our domain, test data analytics, I think we're living in two worlds. And a free lunch world where the OpenRazor as a first principle makes sense, but we can also enter a no free lunch world. And depending on, and when we in the no free lunch world, depending on our assumption, the optimization may lead to different results. For example, with one optimization, we may end up here with another assumption, and we may end up there. So in the DSML, we are dealing with some of the harder questions here, because you can see, first, let me be honest, although I have some success story to tell you, I have even more failure story I can share with you. And over the year, what we learned is that, and often we think about, we ourselves think about the solution before we fully understand the problems. But many times, the real difficulty is that how do we know a solution actually exists? And even exists, how do we know that with our limited resources, we can actually find it? And the problem is that when we cannot find it, how do we know that it is because we did not spend enough resources or the solution just simply does not exist? Well, I don't have answer for all the hard questions about our DSML, but in the last 4 years, we were still searching for practical solutions. And our principle of thinking is the following. If we cannot answer those hard questions, how about try to find a way to avoid them? So in the last few years, we are developing a novel approach as our current solution to the DSML problem we had encountered. And we call our approach describable analytics. So at a high level, basically, we want the user to be able to describe what analytic she and he want to do, and also be able to describe the analytic outcome to others. So let me give you first some assumption we're making in our describable analytic approach. First, we assume the analytic had to be driven by domain knowledge. Then we assume only the user know what result is ultimately makes sense to them or meaningful. A tool can make suggestion, but cannot say for sure it is meaningful. We assume in order to take action on an analytic finding, a user needs to convince others as well. And given all these assumptions, we see that a tool job is to assist or inform the user what happened in the data for them to understand the data, rather than decide if an analytic finding is meaningful for them or not. So in 2018, we wrote a paper called System Level View to Apply Machine Learning. And starting from that point, we advocate in order to apply machine learning in our domain, test data analytics, we need to build a system with 3 components: the domain knowledge component, the concept recognition component, and data preparation component. The domain knowledge component can be represented as analytic workflow. the data component provide option for data selections and pre-processing. And the concept recognition component is where we apply machine learning. In particular, we apply machine learning here to perform what we call plot recognitions. To explain what is that and what is the concept, let's consider two plot examples. The first plot shows a wafer map from the same lot. They all show a failing pattern on the top left of the wafer. The second plot shows an e-test plot, and based on one e-test on two sides. Every dot on this plot is a wafer. The blue shows the distribution of many other. The red dot shows the distribution of the A wafer above. And you can see in this chart that there's a bias of this A wafer toward the bottom left corner of the e-test measurements. So in our concept recognition component, the first type of picture will be considered as one concept. The second type of plot will be considered as another concept. So that's our IEEE 5 years ago. In 2022, we implemented a new IEEE. And the reason is that since then, we've been trying to implement IEEE in the real production flow. And we realized that different companies, even for the same application context, they may want to conduct a different workflow. And even within the same company, different engineers may have their own workflow. Therefore, it's very difficult to develop a workflow universal for all, even for the same problem context. And as a result, we realized we have to keep the actual analytical workflow outside the IEEE. But inside the IEEE, we can still build a component of workflow support, enable a user to conduct analytic workflow of their own. Then that's when we recognize that we need to introduce describable analysis, so a user can describe what analytic steps they want to perform to the tools. So let me give you a quickly go over example of the using wafer map analytics to talk about the describable analytics. So historically, the wafer map analytic is a problem concern the foundry. More recently, the fabless company become more interested. For example, from the wafer pro, we can obtain the wafer map like this. The yellow dot shows the location of the failing die, and you can see some pattern there. And we can also get the color plot as well. And the color plot can either by stacking the wafer map above, or we could pick particular tests and then show the test value. So one of the popular data sets for this problem is the TSMC data set called A11K. Here's some of the examples. In the data set, they define 8 label classes. And there's also one class called none, which is to denote that the wafer map has no patterns. So the point is that given such a data set, it's very natural to treat as a multi-class classification problems. Well, suppose we have a way to solve that classification problem to the best we can. Then in an application, we actually run into this situation. And from the machine learning technology provider, which is us, and this is what we provide, right? So I tell the company saying that I have a machine learning tool that can give you a wafer map classifier with 97% accuracy if you can give me a training data set with a set of defined pattern class. So, and then when I talk to the company from their perspective, and this could be what they request. They told me, say, I have a sequence of wafer map from wafer probe testing. I want to know what pattern are in there. And then if any pattern you find, and correlate to the result from other testing stage as well. So we can see that there's a gap between me and the company I work with. And as a star, I don't know how to explain the true meaning of my 97% to my company's collaborator. Therefore, it's hard to convince them effectively use the technology. And even I can, let's say, bypass that issue. The specific class definition may not be what we want to find a correlation. I don't know what class definition makes sense in this context. And furthermore, the precise meaning of having a correlation can be subjected to the specific user. I know roughly what correlation means, but I don't know the precise meaning of what correlation means, what they want, right? So the reason we encounter gap 2 and 3 is because we're interested in analytics across multiple testing stages. For example, between e-test and wafer pro, and then between wafer pro and final test. what the practitioner is asking is a tool with 3 capabilities: discovering the pattern from wafer probe, correlate the found pattern to the final test, and then correlate the found pattern to the e-test. So let me give you some example of the feed-forward context. So suppose at the wafer probes that we found like these 3 wafer maps with showing these patterns. So that's not enough. We need to want to know the final test, what is correlation. What we can do is to do a stack wafer map here from those, based on those 3 wafers. Then we can see that the stack wafer map that failed on the final test seems like from an inner ring, the wafer probe from an outer ring, right? And this proximity relation can be considered as a form of correlation. And in the feed-forward analytic, getting to the analytic result I just showed you require this iterative process of try and see. And first, we need to find the groups of the wafers showing there's a systematic patterns. We plot, that's easy. And then we need to decide the correlation exists. So this is what we call the try, and this is what we call the see. And due to the time limits, I'll skip the feedback context, very similar. So in short, so our IEEE tool essentially work like, so the tool we proposed, the IEEE tool 2022, essentially work like a virtual assistant. The inputs are user query in natural language. The output are the plots, I showed in the previous example. The IEEE has a natural language front end and analytic back end. The front end implement a constraint parser powered by the pre-trained language model GPT, and the back end implement all these analytic support powered by the machine learning and deep learning techniques. For the 2 components, and we wrote 2 recent papers, and if you're interested, you can take a look. And I just want to briefly mention that in our analytic backend, there's this interesting technology called, we call it minion analytic. So the idea is the thinking is very different. So given the set of wafer maps, we have a way to learn a neural network recognizer for every individual map. And what that gives us is a so-called mutual recognition graph. And once the graph is there, we can perform all subsequent analytics based on the graph. Let me give you an example. Here is a recognition graph example as a kinetic components. On such a graph, for example, we can find a click connecting the, we can find a click, and the kinetic component we're showing here, the click represent an upper bound and a lower bound and what we can describe. For example, in between these 2 upper bound and lower bound, we can describe and identify a describable set of the wafer maps. So let's take a look at the example in the forward analysis. Is some of, I think I will need to, just give me 2-3 minutes, I'll finish it. So this is some of the example of how it works. So we can provide a query, say we want to look at something from 7 to 11 o'clock. Internally, the analytic backend will produce, and then because we try to do correlation, so it will produce this key map as well. Then we can also produce, for example, this is the query, and we can produce this type of correlation plot. And here's a very interesting result that our IEEE tool not only can take user query, but also can describe what you see the pattern. And you can ignore the author's part. Let's look at the GPT-3 part. And for example, for this pattern, what the tool output will say, I see there's a thin arc at 12 o'clock along the edge, and extend to somewhat solid big cluster located upper right at the center. And for example, this one say, I see there a short thick line, which is straight appearing at 8 o'clock point from the edge to the center. And there are most examples like this we discussed in the paper. So let me go to the conclusions. So in conclusions, our research investigate our particular type of TSML in the application context originally from test data analytics. And we see that the IEEE 2022 describable analytic is a way to apply machine learning. And our main thinking now can be called describable analytics. And what does that mean is that in analytics, in our analytic domain, if we cannot describe what we do, we simply ignore it. In other words, we have to be able to explain in natural language every analytic step we are taking and how to get to the finding. So if you give me 1 minute, if you allow me, I will, conclude my lecture today with a remark. Well, after almost 2 decades, I'm a kind of old man now, working on these domains, learning, machine learning. I think the most difficult learning problem I ever encountered is the following. And so if you think about life, it's very much like learning problems. I must say it's a very challenging one. And say in my life, I take myself as an example, at the age of 20, I observed some initial evidence, then I asked the question, should I be a professor? And of course, when the time goes by, a lot more evidence review at the time of 60, when I'm now, then in retrospect, and I can ask the question, do I still want to be a professor? So I suppose that the answer to that question depends on what school of thinking we're following. So if you ask a guru believing in machine learning, he probably will say, I have the best optimization you can follow to make the best decision. If you ask the guru believing in open razor, he probably will say, just make sure your decision is the simplest based on the information you had at the time and believe that there's nothing more you can do. If you ask a guru believing no free lunch, it will say that there's nothing you can do. Your decision is no better than random. And if you ask a guru believing quantum physics, I say the answer might be, I don't know. I think you just need to believe. Well, since I don't follow any one of the above 4 schools of thinking, if you ask me that question, my answer would be, that's actually a wrong question. And thank you for your attention today.
Yeah, thanks very much for the great talk from Professor Wang. I think it's a great introduction on machine learning for yield and test. Especially, I personally think it's very interesting to think about the correlation between the traditional machine learning and the domain-specific machine learning. I do see some of the questions in the chat box. Probably I will.
Yes, I do see. Comment on the technology migration. Can the method and model work across different technology? Well, that's a very interesting question. I don't know the answer because I think in some case it might, some case it might not. The difficulty is always knowing when it can or when it cannot, right? So I don't think there's a universal answer saying you can when you build a model, you can migrate to the technology. It really depends on the underlying, again, it's the underlying the mechanism to the data generator. If you think about data generator, ask yourself the question, but it's not about just the data generator, because different data generator can generate the data that have a very similar behavior. So what we're really asking is not because the data generator are different that we cannot learn. Is that if your data generator is different and when you migrate to new technology, your underlying data generator can actually generate some data which is not predictable. It's not predictable by the original data set from the data set. That is the question where we need to ask whether or not it's predictable. And if you ask that predictability question, that's what I talk about in many of the problems we encounter. And it is really the ability to say no, right? If you do an experiment that with one data set versus another, and then you say, based on this data set, you have a method to say, it's, based on this data set, I cannot predict that, a phenomenon in that data set. And that's the ability to say no. And that's what I keep talking about in today's lecture. And I don't have an answer to the problem, but I think the direction to approach the answer to that problem is to think about how we can find a way to have the ability to say no. Basically, there's no learning model is suitable from a given data set. And the second one, thanks for in the field of machine learning for tests, what could be a possible solution to the problem of lack of data and the long tail imbalanced data set? Well, the lack of data, certainly the answer I think is domain knowledge. And if you think about imbalanced data set, you can the imbalanced data set, I think that you still need domain. I mean, all these things require domain knowledge. For example, one of the things we tried before is that you can use a lot of data augmentation technique. But data augmentation technique, when you use it, you need to be careful not to just follow their algorithm to the heart. you need to look at their algorithm and then try to inject your domain knowledge to see if the data you generate really try to capture the the statistic you want to capture. And so I think how do you generate sample, right? When you have a small data set, how do you generate sample which actually makes sense? It's not just based on some simple statistical assumption, underlying assumption, but actually incorporate some domain knowledge, knowing that that's what I care, and I want to study that particular corner, and I want to direct my data generator to focus on that particular corner. And I think that is an interesting research direction. So my short answer is that we need domain knowledge-driven data augmentation approach. And the next question is, thank you for presentation. It's possible to consider hypothesis space by considering probability occurrence. If so, what about using typical set to focus on it to find the most probable and suitable answer? Is it possible to consider? Yes, that's what people do, that usually consider hypothesis space by the probability occurrence. So that is the problem, right? When you're doing learning, you learn. If you think about frequency of statistics, if you're doing learning, you're learning the trend or the significant behaviors. But a lot of time, depends on the problem you're dealing with. If that is what you're looking for, I think you can certainly use a typical set to do it. But if the problem you're looking, if the value of doing this data analytics is to uncover something like on the tail or something unknown, then a typical set is actually misleading, because what you see is a typical behavior. But sometimes, so it depends on what the problem concept. Do you care about typical behavior? Do you care about abnormal behavior? If you care about typical behavior, yes, I think that is what usual machine learning is trying to do. But in the problem I'm working on, I call it the domain specific machine learning. Almost in all cases, we care about abnormal behaviors, not the typical behavior. So that's why all this no free lunch, all the difficulty I talk about. Okay, and that's a very great question. Could you comment on the trustability of using machine learning model in tests, especially on functional verification and outlier detections? Well, I don't think the trustability is the issue, because in the functional verification and outlier detection, those things are done in-house, which is limited to, even though they have this verification. But if you ask me about if you want to put the model on chips, then yeah, if you do it in-house, I don't think trustability is a concern. But I think what you're asking is that if we take such a model and put it on chips, right, and then do some intelligence kind of adaptations, then what the trustability can be an issue. Yes, definitely, the trustability will be a very big issue, and I think that's why I think there's still a long way to go before we could practically implement that kind of thinking. Did that answer? Because we know machine learning model is kind of right. There's a lot of holes, right? You can actually break it. It's not very robust, and it can give you prediction. Does that make sense? All these issues that is very, I think, is still being investigated and try to solve. That's why I think all these questions are very, is very good. But you can see, in my view, those are hard questions, right? I think it's great research opportunity, but what I presented today is that if I want to build a practical tools, I would tend to find a way to avoid all these questions. So, in a sense, I'm kind of trying to escape from those hard questions.
Yeah, thanks for answering those questions. Yeah, it would be great if you could still stay a little bit to answer more questions if there's any in the chat box. Yeah, thank you. And right, due to the time limit, probably we'll move to the next talk. Yeah, thank you, Professor Wang.
Okay, thank you very much. Thanks for letting me to share.
Okay, thanks very much, Lisi, for your wonderful talk. And our next.
Thanks, David. Yeah.
So, so far we have had two great talks, one on manufacturability, another on yield and testing. So now our next speaker, actually our last speaker for the entire seasonal school is Professor Mohammad Shafique, and he's going to talk about reliability and security, which is also very important. So Professor Shafique is currently a full professor at NYU Abu Dhabi. He got his PhD degree in computer science from Karlsruhe Institute of Technology, KIT, Germany, and in 2011. So before joining NYU Abu Dhabi, he was also a professor at TU Wang and Vienna as a full professor. So his research has been on various aspects, and currently he's leading the eBrain lab, which obviously works on some machine learning. And he also works on other AI and robotics and cybersecurity, etc. And Dr. Shafique received many awards, including the prestigious 2015 ACM SIGDA Outstanding New Faculty Award and AI 2000 Chip Technology Most Influential Scholar Award in 2020 and 2022, among others. Shafique, are you there?
Yes, I'm there, and thanks, David, for the kind introduction, and welcome everyone.
Yeah.
I hope you can hear me properly. Can you hear me?
Great.
Okay, perfect. Then let me share my screen. Okay, I go to the full screen mode. Is it okay now?
Yeah, looks good. I just do the presentation mode. Yeah, everything good.
Perfect, sounds good. So, so welcome everyone, and thanks for the kind introduction. And of course, I mean, it's an honor to be part of this forum, and I hope that I can give you a good talk at the closing and keep you motivated. And what I plan is also that I'll give you some pitch about the open research challenges. And this is the work which is done primarily at my teams in TU Vienna and at NYU Abu Dhabi, the closing one. You will see that last work that I'm going to present at my teams in NYU and NYU Abu Dhabi, and also at part of different centers where I'm actively taking part, for example, on cybersecurity centers, AI centers, and quantum computing centers, and cities as well. Some of the works that I will be presenting to pave a foundation has been done at my earlier stage at KIT together with Professor Henkel. So you'll see that I'll be pitching that how we move from traditional cross-layer techniques for reliability to all the way up to machine learning based techniques for implementing that. And I will also pitch that many of these techniques that we are developing, these systems are actually modern systems, are AI and smart systems. You will be seeing that even for the machine learning techniques, doing a lot of advanced design and optimization also leverages the traditional or high-end machine learning algorithms. So you can call it as ML for ML kind of things, and they are extremely important because machine learning inherently provides a great opportunity for you to develop certain black box model, which can be seen as a strength also, and capture the interesting features of some unpredictable, complex or large scale systems, which are not that easy when we are looking into, by human crafted features, or when looking into, for example, some combinational algorithms or not. So in general, if you look at the modern landscape of the applications, we see the smart prefix coming everywhere. For example, smart traffic control, smart automobiles, transportation systems, smart healthcare, industry 4.0, robotics. And we are developing chips for all these smart systems. And you know that most of the applications that we are developing chips for is actually different forms of neural networks or other kind of machine learning algorithms. Now, in general, when these kind of devices are being connected more and more, there are like billions to trillions of sensors which come into the play. AI and machine learning in general is inevitable to efficiently infer knowledge from the big data and derive predictions. On the other side, we also can leverage this property to understand the properties from extensive profiles of power, energy, and performance of these chips, which is again an extremely complex task. And I'll hopefully will give you a little bit pitch about the performance estimation using machine learning techniques also. Now, when designing these kind of smart CPS IoT systems, I believe that besides performance, energy, robustness is one of the also first-class citizens that we have to consider, because most of these systems are now, as they are integrated in a real world, form some kind of criticality in the integrated system. And this is also reliability and security threats. Besides that, safety, privacy, and all those kind of stuff are going to be there. Now, one can see that, of course, in incorporating reliability and security proactively into the design. But on the other hand, you will also see that validation, verification of these systems is an extremely complex thing. And machine learning is also stepping in the validation and verification of these kind of systems. So you can see that the landscape of utilizing or leveraging machine learning concepts or as a toolbox for design, verification, analysis, and optimization of these kind of systems is huge. Now, again, robustness, I mean, it's a pitch of that there's a diverse range of robustness threats for all these machine learning systems. And that's why, we have to be considerate about what we are putting into the chips and what we are using it for. So challenges, I think in the traditional community, we all know that the complexity of these networks is very big. So there are diverse challenges with respect to compute engines, throughput, performance, and energy, on-chip and off-chip memories. And we as an EDA community are very well aware of these kind of things, that how to design efficient chips, how to design efficient memories, and things like that for even complex systems, and besides also looking into the new emerging trend. So in today's talk, I'll go a bit more different from my traditional expertise. Like, I mean, originally I come from low power community, and I have plenty of work on architectural design and energy efficiency, but I'll go a bit more on the reliability and the security threats, where we see that ML can play a big role also in developing tools and techniques for that. So I hope that many of you are already aware of that we face permanent chips for these faults. I'll talk about that, what happens if the permanent chips happen for the machine learning models. We also encounter soft errors. I'll come into a little bit in details of what are the impacts of that, aging and variability threats. On the other hand, in security, we have new type of vulnerabilities for these machine learning systems, like data poisoning attacks, which can be done on the training side, or adversarial attacks, which can be done on the inference side, or there can be traditional side-channel attacks, and they become much more powerful for the ML systems because since they are black box by in nature, we can actually exploit a black box side-channel attacks to also learn a lot of stuff. For example, learning or the IP of your deep neural network. And again, all the hardware intrusion and those kind of stuff, so I'll come into this in a while. So the challenging question that we always target is that how to process the huge amount of data in robust, energy efficient way for these machine learning systems. Now, let's go a bit deeper so that we can see that what kind of robustness threat exists and what kind of solutions that we can devise for it, considering both traditional as well as ML-based solutions. So soft errors are actually the randomized bit flips, and they can come because of intrinsic and extrinsic effects, like could be voltage noise, or could be neutron or any kind of particle strike that can happen to your transistors. And it can lead to random bit flips, and in memories, we know that they can be lashed, and then in combination logic, they can be propagated or masked. Aging, on the other hand, there are different types of aging like TDDB, HCI, but this is one particular that I'm showing is NVTI, which is a negative bias temperature instability. This can lead to, for example, increase in the VTH that ultimately, in a layman's term, will lead to the slowdown of your transistors. Variability is another design challenge where you do not have one fixed frequency or a power consumption of one core. Rather, there is a complete variation of these factors across the chip as well as across different chips in a wafer or across different wafers also. And the last or not the least is the computational the thermal hotspots that we get, and because of these thermal hotspots, the chips can burn down, or the reliability can also be aggravated. So just to give you an idea, that temperature can be seen as a catalyst for many of these aging factors. For example, this graph shows that with increasing temperature, electromigration can increase, or time-dependent dielectric breakdown can also increase, or the thermal runaway problem, which means with the increase in temperature, your leakage can increase, and consequently, it can further increase the temperature. This is a graph which shows that with increase in temperature, the impact of NVTI aging is also higher. And over the years, this can keep on increasing, which is termed as long-term aging. And of course, there are short-term aging effects as well that a lot of other groups are exploring, including Henkel's group. And then there is also this thermal stress that inherently comes from this thing. So temperature optimization is one of the primary goals in many of these multi-core and many-core chips, and even these heterogeneous chips where accelerators are coupled with other kind of general processors. Now, but in general, temperature optimization or temperature-aware reliability optimization is a complex problem because there are many different factors involved into this thing. And we'll talk about that, how this can become an issue when we're talking about scalability, when we're talking about unpredictability in the thermal map estimation or in the performance estimation of these different applications. One of the side effects that we have seen from the temperature is the emergence of the dark silicon problem. And we know that, I mean, with the breakdown of the classical Dennard scaling, the voltage is not scaling proportionally to your transistor scaling. And that's where the power density, which is the power per area, is kind of increasing exponentially with the continuous integration of many small scale devices into a chip. And you can see that with this study, people estimated, this is quite old kind of study, but people estimated that the amount of dark silicon can be, close to 50% of the total chip. Now, this kind of scared the whole community, and then people started looking into how to exploit this dark silicon in many different ways. So some people started talking about the importance of the accelerators, so which are extremely energy efficient and do not produce a high power density. So a lot of this silicon, instead of using a general processor or extending these processors with vector units, we keep on designing dedicated co-processor block, for example, for NPUs, neural accelerators, video processing cores, or image processing cores, and these kind of stuff, or graph processing cores and things like that. And on the other side, people started exploiting these dark cores for the thermal dissipation, putting more and more memory into the chip so that they can be used for the lateral heat dissipation and devising those kind of stuff. So in general, dark silicon led to many different architectural optimization and new trends that we see today. So mitigating aging and variation, I'm not covering the whole range of the state of the art. Like there is more than 30 years of research into that, and many of the participants that we see here are pioneers in these areas. But just to give you a little bit coarse-grained coverage of that, mitigating aging and variation, the trend which has been widely used in industry and also in research is, for example, introducing guard bands. And there can be many different guard bands, PVD guard bands that people introduce. But ultimately, we lose something by introducing these guard bands. So how we can optimize these guard bands so that we find a trade-off between optimizations and performance loss that we ultimately pay off. Then comes the workload management. Of course, the controlled use of these cores will also lead to some kind of optimization, but these kind of techniques are software or variation unaware, and it might happen that you are optimizing for aging, but you aggravate the system for soft errors. Now, mitigating soft errors also has been done for more than 3 to 4 decades. And we have seen very traditional solutions from redundancy based to all the system level redundancy as well as instruction level redundancy techniques that happen. But many of these techniques can either aggravate aging or aggravate thermal profiles that we can see. Now, the thing that we study typically is there is a need for cross-layer reliability approach that leverage the knowledge from multiple system layers to address multiple reliability threats. So I'll quickly walk through that some of the techniques that we have explored just to pitch that cross-layer factor is extremely important when we are talking about the joint mitigation of multiple reliability threats. And then I'll come forward and see that what kind of techniques can be can exploit the traditional techniques, or what kind of methods will require machine learning. And so we don't need to overly claim machine learning can solve all the problems. Sometimes it is not even necessary or required. So this is a bigger picture. I'm not going to detail of this thing, but this I will give these slides, but this provides a summary of the major works that we have done at KIT in the GetSure project, where we have looked into the design of reliability heterogeneous cores. We looked into play of the DVS and task management and those kind of system level techniques for optimizing the thermal maps and ultimately the aging optimization. We have looked into some compiler frameworks for generating different diverse variants of programs so that we can see that how they vary with respect to their software resilience as well as aging. And then can we generate different tasks with different compiled versions or compiler optimizations that can be then exploited at runtime for example, for balancing with respect to software as well as aging. So all this, given hardware and software, we need some kind of operating system extensions, for example, reliability aware DVFS, reliability aware task migration, aging awareness, and the variability awareness in the cost function of these kind of task management algorithms and things like this. So the underlying rationale behind this is that different applications have different resilience properties. There is no single silver bullet for everything. We have seen that different applications, due to their diversity in the control and data flow graph, they lead to different distributions of, for example, complete program failure or correct output. And this is because of the inherent masking effect of many of these applications. So I'll just quickly walk through that. We don't need to go into details of that. But bottom line that I'm trying to say is, if we generate cores with diverse hardening methods, we can realize a trade-off between an area that we have to pay and the power that we have to pay for protecting these different components of the cores versus the resilience and vulnerabilities of these tasks that we can obtain through different compiled versions, as well as running on these different variants. So exploiting this principle, we proposed first this ACER approach, where we kind of made different or designed different IPs, different versions of, for example, this RISC-V core, and then we extended them different hardening components, for example, protecting the register file versus protecting the pipeline and things like that. So just to give you an idea, this is, for example, a different versions of these different cores that we generated from the Wang baseline core, and these are the power profiles and the area for a 45 nanometer technology that we use for synthesis of this thing. Now, given such kind of system, you can realize many different applications. But taking one step back, there is also a regular homogeneous multi-core systems. So what we can do for those kind of systems, and we know that a very prominent technique that I think in earlier times Intel proposed was the redundant multi-threading, which is an RMT approach, where you can use 3 different cores to realize the redundant threading, and then there is in a log step you can compare them. So the biggest issue for this is that for any given core, you can only facilitate a certain number of applications for that, and all the other kind of applications will not be facilitated with RMT. So which application you want to run with the redundant multi-threading, which will not, is again a question of the resilience that you will do that. So we developed a solution which can effectively activate or deactivate RMT based on the resilience properties of applications. And since these properties can vary over the period of time, we can maintain or monitor the history of errors, and then we can upgrade or downgrade an application for getting either an RMT or deactivating it for that. And we have also analyzed that by generating different variants of this application codes, we can in general save RMT from some of the less critical applications and then give this budget to, for example, more critical applications. So give you an idea about how the results look like. You can see is that we compare this approach for the CRT approach, the adaptive CRT approach, another cross-layer approach. And we can see is that the different years of aging, the main approach, which is the red line, you can see is that the percentage reliability improvement is significantly higher for our approach compared to the other one. And that's because we can learn the behavior of application, and we can exploit the diversity and the resilience properties at runtime directly. Now, having said that, this is only one side of the picture, and we know that there is a variability, which is the second side of that picture also. So not every core is exactly the same. So what we did is that we analyzed the same study for different variation maps, and we saw that actually because of the availability of different frequencies, and when considering the critical systems where we have deadlines, in some of the cases, finding a feasible solution may not be actually even possible. So, and the reason is that because we did not care for the aging of the slowest core, and in that particular case, it may happen that those slowest core are then dubbed as the failed cores eventually, because some of the applications just may not use them due to the deadline constraints. Some other may be able to use them, but some of the cores cannot use them. So we just did that. We in the previous work of the DTune, we just integrated the variation in the cost function, and by doing so, what we did is that we basically improved the minimum frequency of the core, and we basically bridge the gap or reduce the gap between the maximum frequency and the minimum frequency, and in this way that then the number of cores which can be used for all type of tasks actually is increased over the period of time. Now, bottom line of this initial study was that the cross layer is the key. We need to understand what is available at the software layer, what are the resilience properties of these applications, what we can exploit in the compiler, how we can generate different things at the compile time, what kind of hardware architectural extensions are required, and then what kind of runtime system is there. Now, for the early stage of the work, this is okay, But as we move of these kind of systems is an extremely complex and time-consuming thing. So can I use machine learning for accelerating this thing? So what I'm going to show you is a little bit of the work that we have used to implement a scalable and machine learning based task management system for improving the aging of this stuff. So general flow of that, if you see here, is that we take applications, we do profiling of these applications, and then we run them on this multi-cores. And there are two main components where one is the aging estimator, that is the dynamic resource management. Now the profiling, aging estimator, and the dynamic resource management, all these three components can be done using ML-based techniques or can be done using a non-ML-based techniques. So the first thing that I'm going to show you here is actually a ML comp work in which we have used different ML-based performance estimation techniques. And what we have also studied is that there is an impact of different compiler optimization sequences, like which is called a phase ordering problem in general in the compiler community, which means in the way that we are applying these optimizations can eventually impact your performance, energy efficiency, and resilience properties. Now, the question is that it is an NP-hard problem, because if I have like 50 different compiler optimizations, and if I do optimization 1 first and optimization 2 second, and if you just switch the sequence, the code is very different and the properties will be very different. So how do you give me a Pareto optimal phase ordering sequence, and how do you estimate the performance of that? Because this is like a numerous number of combinations of profiling that I just simply cannot do that. So what we did is that we developed a framework, and this was done together with Axel Jar's group and an industrial partner in my group in TU Vienna, where we developed an end-to-end framework, also within the industrial simulator. And this work was actually part of that project. So what we did is that we first extracted the data through extensive profiling for a given platform, and we targeted 2 IoT platforms. One was on risk-based, another was a small, tiny x86 based kind of framework. And we extracted different features, and these are features on the IR, which is the intermediate representation of a compiler. And then in the second stage, we explored many different machine learning models. And we have like, I think 10 or 12 different models that we considering random forest search, considering regular ANNs, DNNs kind of stuff. And then we started learning different models for estimating the performance, so that we do not need to do extensive profiling. And if we have the IR features from a compiled program, then we can already give you what would be the estimated performance of that for a given platform. Once we have this kind of model, we can actually use this model to even predict the compiler optimizations at the static time, because at that point in time, the compiler is not doing any dynamic profiling. So we can embed this model. So this model can be used in 2 different ways. One, extending the compiler to figure out a nice phase ordering sequence. On the other side, even fast evaluation of the different programs. Now, in the phase selection problem, we have employed a reinforcement learning based model, and we actually identify what is the set of Pareto optimal points for us, and what is the optimized code that can minimize energy efficiency, maximize the resilience, reduce the performance estimation time. And then in the last stage, we deployed on a real IoT platform, and then benchmark it, and then compare it with our estimation also, so that we can see that if the runtime data that we generate is eventually fulfilled with our actual model that we generated that. So this is, I think, is a classical application of machine learning for many of the offline problems that we do, because they're extensive in nature. Just to give you an idea for different type of benchmarks, you can easily see that the ML comp and the actual real profiling with the dynamic profiling is actually pretty much similar. There is very hardly a difference between that. And in the bottom line curve, you can see is that pretty much this stuff is overlapping. Now the whole process takes less than 2 days to generate this thing. The benefit is that we have an automated data extraction kind of pipeline, and this is highly usable for that. So again, we did much more detailed study with respect to energy, memory size, and execution time, all these kind of aspects. There are some outliers. You can see here is, for example, in the energy part, there are a little bit of the outliers, but overall, the execution time and the memory size is pretty much same for us. And even the phase ordering gives us an extremely nice solution with respect to that. Now, this kind of tool provides a lot of benefit in general for doing compile time optimizations, doing static evaluations for your program and things like this. Now, going one step forward, how we can make these kind of techniques scalable for reliability management, and how the machine learning can play a role even in further learning the policies in unpredictable scenario. So I'll step by step build up the ground. So first, let's assume this is the work Hayat, which simply does a patterning, solves a patterning problem to maximize the health condition of that. And you can see in these two curves where we have contiguous allocation, this is one type of approach, versus a patterned application, we have a little bit improvement in the average frequency of the overall core. Now, in this whole system, there are two big problems that we have to solve. One is the health estimation of these maps, which is you can see here in the middle. And this requires, for example, a complete thermal map that we have to estimate at runtime, because we do not have those thermal maps before running the actual application, but we need to solve optimization problem to identify a pattern, so that if I use that pattern, then my health will be optimized, my temperature profile will be optimized. So for that, what we did is that we created some kind of thread maps, which are 3x3 maps, and then we did some kind of superpositioning of this thing. And I think I can just show you with the help of this thing. So we did a superpositioning of that to estimate a map. But this is kind of okay if we have a linear system, but we know that thermal prediction is not a linear problem that we have to solve. So there is some kind of nonlinear effect comes, and one of the major effect of this could be the leakage power, which has a feedback loop into this thing. So what we did is that we basically have some kind of refinement factor. You can see it as a delta, and this delta we learn using a very simple statistical inference kind of methodology, where we have a data set generated and we learn a small delta factor that is uses, for example, a correction factor that we can apply, and then we can obtain that. So to some extent, this is a very accurate thermal map that we get, but still it's not 100% accurate. Of course, there is inherent prediction loss that we will get. But bottom line is that when using this kind of stuff, compared to only variability aware mapping, Hayat already significantly optimized the aging rate of different cores. And I think this curve actually shows very nicely. If you just do a contiguous allocation versus Hayat, you can already see that lifetime improvement with some factor, for example, 50 megahertz improvement in the overall frequency after 3 months, while it can be a little bit more when you are considering over 5 years of aging. And this is the gradual deceleration of the impact that we see. Now, I think this curve, this graph, or this picture that we are presenting now shows how the evolution of these techniques work. So on the left side is Hayat that I showed you, which tries to disperse the task as much as possible in order to alleviate the dark silicon effect. On the other side, the contiguous one tries to keep this common. Both have their own pros and cons. When you have the tasks which are very dispersed, you spend a lot of power in the communication kind of part. So HiMap actually tries to find a in-between solution where it solves a binning problem, and then tries to first map applications to a big cluster, and then inside the cluster optimizes or solves the dark silicon patterning problem. So in this figure, you can easily see that, for example, the application A3 has different tasks. They are assigned to one big cluster, and these are kind of closely or close to contiguous, but there's still some patterning. And the A1, for example, in the top right corner, and then there is internal patterning which is there. So this gives us a little bit trade-off between I think I go one slide back. This gives a little better trade-off between Hayat and also the contiguous kind of stuff. And you can see here is that the purple graph, which is HiMap, is a much more balanced aging profile compared to the, for example, the runtime mapping approach with the contiguous versus this thing. And HiMap also gives you the minimum MTTF compared to the both approaches. Now, one problem that we have faced in HiMap is that it lacks kind of I mean, it is extremely important, and to notice here is that when we are solving the optimal problem, for example, using simultaneous annealing, HiMap still is much faster because it does a kind of a divide and conquer kind of, policy there. So it's close to kind of a greedy approach that you can think of. And it is highly scalable in these scenarios. But the biggest drawback of this thing is that it is a one-time mapping thing. So if your parameters of the system change, this policy is still static by nature. Though it does dynamic decisions, the policy is static. And we have seen that there may be a requirement where the policy needs to be learned over the period when, for example, your application patterns just change, and your for example, design rules or design metrics can change over runtime. So Lifeguard is actually RL-based extension or enhancement on, you can think of as a high map kind of stuff, but overall inherently it optimizes the internal design flow also. So there is a traditional approach which was proposed by Das at DAC in 14, which uses the reinforcement learning to take decisions about temperature optimization or thermal optimization, inter-task and inter-task. But what they did is that they formulated the mapping problems as an action. And the issue with this kind of approach is that the action space grows very big if your number of tasks and number of cores are very, very big. So on the contrary, Lifeguard actually maps this to the decision logic and based on the application or exploiting the application knowledge, which means that we are learning the policy based on the categorization of the application and not for every task, not for every number of core. So in this particular case, you can see the result that the action space of the Lifeguard is extremely small compared to the other approach that we have. Now, overall algorithm is pretty complex in the flow, but it's very simple to implement if you see that. So I'll partition into two course grain steps without going into detail, and we can discuss these details later on. The first one is a bin formation. So what it does is that it forms the bin based on the maximum frequency which is required by a certain application. And what are the maximum frequencies that we are talking about? So for example, if a task requires a minimum frequency of 1.5 megahertz, someone has to meet that requirement and it should not be violated that. And then based on this thing, we are trying to do that. Now, there are different tasks which can use multiple cores because those cores meet their requirements, and some tasks may not be able to use certain cores. For example, they need a super fast core or turbo boosting kind of stuff then in those cases. So what we do is that after the initial mapping, the RL learns that policy, and then we have a learning interval, for example, after 10 minutes or after 100 minutes or after 1 hour or things, or maybe after a few hundred milliseconds. That depends upon how you define the learning intervals. The one decision or one policy from this table is selected, and it will be continuously used throughout the learning period. And during that period, we are updating this policy table and we are learning new policy. And once the new policy is learned and once a completely new different use case scenario comes, we can pick a policy and then we can adopt that policy and then we can give you the minimum MTTF. Now, if you look at the bottom left graph, which is the first one I want to tell you is that the aging optimization is kind of very similar to the high map kind of stuff, with in some cases where high map has the best aging compared to the Lifeguard. But the benefit that we get is that the frequency of the unfilled cores, an unfilled core we call it here, if there is a core in which the aging has happened such that some of the tasks cannot use them, this is what we aim to minimize, which means that we achieve a much balanced aging profile with the probability of a certain core facilitating or servicing a given task is the best one. So in this particular case, Lifeguard actually wins, and the key is to exploit the ML things. Now, in the modern works that we are doing is this is the work that is traditionally for the multi-many core systems, but now the most of the recent works that I'm doing is primarily doing the resilience or reliability of machine learning IPs, and there we are now stepping into also using machine learning based techniques for ML resilience, and this is what I will touch at the end of my talk. But before going there, I want to also tell you that how we can embrace machine learning techniques for hardware security. And this is the work which is done with one of my colleagues, Ozgur Sinanoglu, and his postdoc, Lilas, together with some of the other collaborators at US Union Schools, for example, Shafique. So what we are doing is that we are embracing graph neural networks for the hardware security. And we also organized recently a special session at ICCAD where we invited different persons to discuss that how graph neural networks can be used for EDA. And I would like to also take the liberty of this talk to emphasize that GNN has a great potential to service different EDA problems. And this is, of course, at some point debatable. I think many of us will agree that. The reason is because circuits can be represented as graph. Now, in general, graph neural networks have been shown as a great success in many different applications where those applications can be represented as graph, like social networks or protein-to-protein kind of interaction graphs, or any kind of applications in bioinformatics or in social networks. Now, circuits inherently we know they're graph, and if you look at the EDA, we are actually solving a lot of graph problems or tree problems. So in this particular case, we can transfer a graph, a circuit into a graph, and then we can start using GNNs for solving many different EDA problems like static timing analysis, chip placement, on chip routing, and things like that. So I will refer you to the recent ICCAT special session that we organized. Many different speakers talked about different aspects of GNNs in different EDA problems, and you will be able to learn that how these GNNs can be used there. But in rest of my slides, I'm going to talk about the use of GNN for hardware security. We are the first ones to explore that together with Ozgur's team. And the security, what I'm particularly talking is actually the in reverse engineering kind of stuff. So we know that traditionally why hardware security is an important thing because the IC fabrication costs are exponentially increasing. You can see the 5 nanometer fab cost is $5.4 billion compared to $2.9 billion for a 7 nanometer. And earlier, these different steps like chip designing, fabrication testing was done at by one company in-house, but now this is like distributed across different companies and different expert companies, I would say, across the world. For example, let's assume AMD designs a chip, fabricates using TSMC, and testing is done with the ASE. Now, when we are talking about distributing these kind of stuff across different companies, the insecurity increases. And this graph, for example, shows that where most of these kind of services are provided, for example, IC design in US, and the wafer fab, for example, the machines are done with ASML. Most of the fabrication is done in China, and then testing and other kind of stuff is done in different other countries. So the hardware attacks that we typically see is counterfeiting, which means making a fake chip, and IP piracy, stealing the IPs, overbuilding. Someone is excessively producing without telling the vendor, and hardware trojans, which are inserting fake circuits inside your actual logic. And reverse engineering also is kind of way to basically learn the circuit of your chip and then doing all the above attacks and things like this. So in this, in the next slides, I can go all over other threats also, but in the next slides, I will talk about how GNNs can be used for reverse engineering as well as IP piracy. So the first thing, I think sometimes the Zoom hides my title. Okay, I'll just put it here at the bottom. So the first thing that we get is the netlist. We transfer this netlist into a graph structure with the node features. And one thing to identify here is that the graphs, neural networks can actually learn interrelationships between different nodes. So they can be local features, they can be global node features that we can learn that typically we just do not even envision as a designer sometimes. So these learned features are sent as an embeddings, and then from there we can do some kind of classification to decode some knowledge, to do some attacks and things like this. So the downstream tasks which are done typically are detecting hardware trojans. So people have done that. UCI has some work in this thing. Detecting IP piracy, functional reverse engineering, as well as attacking logic locking. So I go into the reverse engineering attacks, for example, in this thing. The general theory about reverse engineering is that we can take and unpackage the IC and then step by step do the delayering under the electron microscope, do some imaging, and do the gate identification. Once the gate identification is done, we try to build a netlist and identify those blocks inside the netlist. For example, this can be comparator, this can be a multiplier, this can be adder. Now, graph neural networks provide a very powerful tool to learn those patterns from these kind of components in the reverse engineering netlist and tell you that is it a subtractor, is it an adder, is it a multiplier, how does it look like? And then we can identify those sub circuits easily inside this complete netlist and tell you that, okay, here is the multiplier, here is the adder, here is a comparator, and now you can try to learn what this circuit actually is doing in real life. You can go into detail of this paper from Leela's, and then you can learn more details about how does this work. I'm just giving you an overall idea about how the machine learning can be used for that without going into details of the actual algorithms. Now, logic locking, we all know that is a very well-renowned technique and widely used technique for protecting the chip against IP piracy, which means that we can actually lock a circuit with the help of a hardware key, and without this key, nobody will be able to identify what is the functionality of this circuit. So give you a little bit idea what is locking here. You get an original netlist, then we insert some key gates, and these key gates require some input, which is called a key input. For example, K0, K1, and K2 in this particular case. And then unless I don't give it this key, the circuit will function incorrectly. For example, let's assume if we give 0, 0, 0, the answer should be 0. Now the correct key is 100. If I give the correct key 100, the circuit will function correctly. If you give incorrect key, for example 011, certainly the output will be incorrect. So without the correct key, you cannot run this circuit in a correct mode. Now what you do is that you make this or design this circuit and you don't give the key to the fab. You hide the key and you only have the key gates inside, but nobody knows what are your key gates. And we fabricate the chip, test it, and then the activation is done at the IP owner side. IP owner knows that what is the key. So it will embed the key inside a tamper-proof secure memory, and then we'll give it to the end user, and then the end user can use that. So logic locking has been widely used by many groups or explored by many groups as a very powerful technique for locking a circuit and avoiding it. So we are currently looking into, and Oscar has fabricated even many chips which are locked chip, which are proven to be not broken, for example, by the traditional techniques. What we have seen is that where the traditional techniques break or cannot function, and especially in an Oracle-less setting. I mean, Oracle is when you have a fully functional chip and you can compare and find out the circuit. But in Oracle-less setting, where you don't know what is a golden circuit, breaking a chip is an extremely complex problem. So we saw that the graph neural networks can actually learn certain properties which can help in breaking those kind of stuff. So in this particular case, one of the techniques that typical community is using is to identify key leakage gate. So what they do is that they do some kind of local transformation. For example, this AND gate is transformed into a NAND gate, and XNOR is converted into an XOR gate. And by doing this thing, they are trying to realize some kind of bubble push behavior, where they can see is that maybe some of the functionality or the signature of the functionality can be changed. Now, when we have seen that once we do a graph attack on this kind of stuff, we can identify some leakage information from this XOR gate. And the reason is that because the GNN can learn a certain local feature, and that local feature exposes this XOR gate. And once we know the XOR gate, you just need to feed it like 1 or 2, 0 and 1, and with 2 possible combinations, and we can identify the correct functionality of this circuit. Then going into a little bit more powerful algorithms. One of the most powerful algorithm in the logic locking is called provably secure locking. And in this particular case, we can see is that what typically the locker does, it does not give you the original circuit, but rather a modified circuit. This modified circuit is some kind of having obfuscation, where you have original circuit with a perturbed logic, and this perturbed logic disrupts your actual functionality and gives you some kind of noisy output. But you also give a restore circuit with a key. So if you combine the restore circuit with the perturb output, then you can get the correct output. An attacker goal is to find this original circuit, because if I know the original circuit, I don't care about perturb and restore. I can just fabricate the original circuit and this will work. The perturb and restore is to fool the attacker. Now, in the original design, they can be mixed up. If you look at the features before GNN, you can see those all features are mixed up, like red and blue and green are there. But we have learned a graph neural network, and once you dissect the embeddings of that graph neural network, we can see is that they are actually completely separable feature spaces or embeddings. So we can separate completely the red ones, the blue ones, and the green ones. If I can separate the green one, I can already decipher the original circuit, and even a provable secure locking is vulnerable to these structural attacks. And the key is that because the GNNs can learn those local features from those embeddings. I'll recommend you to look at this GNN Unlock Plus, which is the very comprehensive article explaining the methods and the algorithm behind the whole thing. Then another problem so this is what we are seeing is different type of locking techniques. What we are trying is how GNNs can break many different locking techniques. So one of the latest locking technique is inserting muxes, because mux in general is very, very hard to be broken because of just the probability. I think people have shown that if you insert a mux, the hardness of this circuit can be very, very high. Now, once you have a multiplexer, you can insert false wire and a true wire, and the true wire will only be activated once you give the key. So this is more powerful than an XOR gate, because there is no information leakage happening in the multiplexer. Now, can we find this thing? So interestingly, we looked into one of the traditional neural network community paper and learned that they have a problem called link prediction in incomplete graph. So that link prediction problem says that if you are giving me an incomplete network, I can predict the nodes and can identify the most likely link between that. So traditionally, this problem is like A and B. Does A and B have a link or not? Does C and D have a link or not? So this problem has been solved by the traditional machine learning community. We found that we can actually reduce this problem to our link prediction problem for the mux-based locking, because in mux we can identify that if there is a true wire or there is not a true wire between two nodes. So we designed a graph neural network, trained it for this kind of problem, and then we predicted if there is a link between that, and the link for us would be effectively this true wire going from this multiplexer all the way up to from G2 to G3. And this is what is the one that we are predicting. And we have a very powerful attack that we have done on this thing. Now, conclusion of this part of the talk is like there are advancements in machine learning, specifically in graph neural networks that can solve many problems for EDA, and that can also help us in studying the security vulnerabilities of certain circuits, which are seen to be proven or provably secure, and they are no more provably secure because machine learning just provides a very, very powerful tool. I think some of the, this animation comes. Just to give you an idea of importance, graph neural network papers are exponentially increasing just because they are very powerful tools for graph structures, but also for the circuit paper also increasing exponentially, and because people have figured out that the GNNs can solve many of the EDA problems very nicely. They are like very amenable to that. The one thing that we are looking into is that how the security attacks on graph neural networks can be a problem in the EDA toolchain. For example, if someone is using GNNs for Trojan detection, can I insert something inside a graph neural network that can fool that? If you're using GNNs for example, breaking certain logic locking, can I fool my GNN for not breaking this thing and things like that? And this is the reason because many of these kind of networks are again trained on a third-party service, or if you are looking into a designer toolchain. So that's pretty much end of, let's suppose, most of my talk. And towards the end, what I want to pitch you is that how these kind of techniques are changing or adapting when we are talking about the machine learning systems. So I think I'll just quickly fall through many of people, and this slide I want to show you because many of the people always tell me that machine learning is is extremely robust and resilient kind of stuff. That's true if you're inserting faults or attacking things in a non-critical neuron. But if you are inserting a fault in a very, very critical neuron, a single bit flip can actually destroy your accuracy. And this is done at the bottom, in the left bottom part that you can see. So the current state of the art or industrial practice is doing a redundant cores. For example, in Tesla, they have two AI processors. And this is the main reason, because in safety certifications you need to have a dual processor to make sure that things are safe and things are continuously checked in a lockstep kind of fashion. Anyway, the redundancy based solutions are very, very complex. What people have started doing is that if I can identify, I mean, there are different type of faults like permanent faults, software faults. If let's suppose I have permanent faults in my chip, can I use some pruning and now exploiting the machine learning principles to embrace these permanent faults and then kind of avoid those faults in those chips. The biggest problem with these techniques is that if I just show you one next slide, that if given any network, and since we know that the permanent fault profile are different for different chips, you can see that every time for a given chip, I need to modify my network, which means it's a complete retraining of the network, which is super costly. We all know that retraining is not that simple. So in this particular case, I have to pay for excessively for retraining. Now, in one of the industrial projects, what we were given a job that can I solve this problem without retraining? So we figured out that we can actually do a fault-aware mapping. So we developed a saliency map of different neurons, understood the machine learning resilience properties for a given network, for a given fault map for a given chip. What we did is that we just did a remapping of the weight arrays on these kind of stuff. And then if you have multiple faults, then we can use the sum of those non-critical weights to identify which mapping would work or which mapping would not work. And interestingly, we were able to achieve much higher resilience without retraining. And you can see here is that the salvage DNN, for example, work is providing very close to the accurate case for a very high number of the faults that we are talking about. Now, this tool then we gave to our industrial partner, and then they use that or forward that to their engineering team to test and then use it for increasing the yield of their chips. Then there is another work where we talked about that how we can identify the soft errors in these kind of machine learning IPs. And then what we figured out is that when we are having some errors, and if those errors do not flip my output of classification, let's say A, B, and C remain the same, then there's no problem. But if they are changing my classification, then those errors matter. So we figured out that at the end of the ReLU block, for example, we can identify if the range is shooting too much high, then this is potentially an error, and we can restrict that range in a bounded way. So we did profiling of the activations, and then we determined and derived those bounds formally, and then deployed them in range restriction blocks, which are robust memory components. And then by doing this thing, we devised a soft error monitor inside these IPs, and this again went into restriction block, and I think one of his works even went into OpenVINO. I was just reading some news. So these kind of techniques have a great potential for this thing. So I'll just skip other parts because there is a limited time. I want to take some questions. I'll just skip the aging optimization of this thing. I want to close with this talk with the stuff that we are doing many different security attacks, like adversarial attacks on the machine learning IPs. On the backdoor attacks during the training time, and the piracy attacks on this thing. And you will see that many of these attacks are actually using inherently the principles of machine learning stuff. For example, if I want to break an algorithm, which is a machine learning algorithm, I need to deploy machine learning based techniques for learning the IP, for example, that. So this is what I call is ML for ML. And I think this is inevitable in modern age. That's why using machine learning for many of these EDA problems, many of the system level problems is the future to go forward. So in general, even if we talk about general.
Hello. Hi, Shafique, are you still there? Somehow we. Hello. Shafique, are you still there? Oh, maybe we lost you.
He's still connected.
Yeah.
Maybe he can chat.
Oh, he got dropped.
Oh.
Okay. Hopefully he can join very soon, right?
There he is.
Okay.
David, I think my internet connection broke actually, so I'll just shut down my video to see. But okay, I'm here for the questions. But unfortunately, connection was broken. I have to see if I have the chat questions or not.
Yes,
Okay.
we do have quite some questions for you.
Yeah, he probably can't see them, so maybe Jachi can repaste them.
Oh,
I saw. So I can see some for your ML component. You mentioned 12 different. 12 is a number. I think there are more than 12. We have a full library of these things. What's your criteria for optimal? Slide 36. Golden simulator for different metrics. Are you going to use different ML for different metrics? Okay, very nice question. This is from David. In fact, there are different models that we use in the library. And for energy estimation, for performance estimation, the models can be different. I have to dig deeper into the paper details that which model was good, or I can ask my question. I don't remember this by heart. Optimality, we did not target the optimal as an absolute optimal. It was a Pareto optimal, which means that if there is a solution where I get the minimum performance, can I also have a minimum energy? And this matters mostly for the phase ordering, like sequence. So if I can generate 1 million different phase ordering combinations, what would be the best out of this 1.8 million given my constraints? Now the constraints we got from our partner, for example, if I have an IoT board where I have 1 megabyte of on-chip memory, and out of this I can use, for example, 256 or 100 kilobyte for the instruction memory, then my code should fit within the 100 kilobyte. So that is my constraint, which comes and we actually call them extremely low memory footprint IoT devices. So the whole idea was to reduce the memory requirement for the compiled code for that, and while also minimizing the energy consumption. So this is the case. Does it answer? But of course, I mean, the models can be different for the different metrics.
Yeah, answer my question. Thanks very much.
Okay. Then other question I can, whatever I can see, and then if I miss, then you can say. Could you comment on how quickly dynamically handle the impact of time variant aging issues beyond the static aging map? So if you ask me about, if I understand correctly, you're talking about how we know that if it's after 1 year aging or 2 year aging. I think this is a complex problem in general for the community. So what we did is that we did an accelerated simulation for, let's suppose, 1 year, 2 year. I think I may have a specific slide for this thing, but in general, the whole idea is that we defined that if we have a simulation step, I can keep on simulating that for, let's suppose, for 6 months. So that that workload I can keep as an average workload for, let's suppose, 6 months or 1 year or 2 year and this kind of stuff. Now the aging maps that we got is basically based on some kind of, again, a model, and I mean, they are of course as good as the model. So if you have a better model, you can get the better aging things. This is a long-term aging model. I can refer to one of the papers from SPP 1500 where they have published this model. It is done by Thomas Habe and Jörg Henkel. You can see that that long-term model actually hides many of these different short-term effects. But there is another work from Henkel and Hussam Abrouche who are looking into the short-term aging effects. So we use the long-term model in general based on that work. Tahuri also has some work on the long-term model. And that long-term model gives us like 1 year, 2 year, 3 year, 4 year, up to 10 years of the aging steps. So we can move between different those aging steps, and together with the accelerated aging, we can try to have this dynamism. So there is a mixture of workloads that we can choose dynamically in the accelerated simulation to realize the dynamic aging effects. Variability is we generated many different variability maps based on a model which was again based on a study from CMU, and Siddharth has one of the earlier works in that area. And we used many different variation model generated at the design time, and then overlapped with the aging rates. Then we can realize the dynamic variations in general. What is the resolution of the image? Can someone tell me what does the image mean? I don't know what is the image that you're talking about.
You said you could reverse engineer your net list. So this is Ioannis at Drexel University. You said you could reverse engineer your net list, right? So I was kind of wondering more on the technical side on the resolution of those images. So can you resolve transistors that are 3 nanometers or 5 nanometers to be able to stitch those, to even be able to extract the net list? Or maybe even machine learning could be somehow applied in that area. I'm not sure about that one, but I'm kind of curious on what kind of resolution of images you have that you can actually stitch together these net lists.
Okay, I mean, so the reverse engineering work is primarily from Osgur. So I was presenting this as a general knowledge for the audience. So I can refer to that paper and you can look at that. I think, but mostly they are still working on the netlist level. Like they are given a certain netlist and how you can decipher that. I think this would eventually be dependent on, based on my just reading knowledge, this would be based on the accuracy of your electron microscopes. So how good you can capture those images. So if you have a very good electron microscopes, then you can generate very good images from there. So
yeah, I was
just
sorry, yeah, I was just kind of wondering about that because you know, a lot of people talk about the reverse engineering, how you apply all these techniques to it, but the netlist extraction part is always kind of, you know, a lot of it's dependent on that extraction, but that's not necessarily a easy task per se because of resolution of images.
Yeah,
but
I think Shafique's is more from get level to the like a functional level, right? He's reverse, right? Yeah. So, and I just posted a message there, right? We also have some work on from GDS2 to get level, right? So I guess ultimately we can kind of from get level, then I think using Shafique's technique to do, like he's detecting adders or bigger structures, right? Is that right?
Yeah. So again, just to disclaimer, this Osgood work, I mostly work on the GNN for the logic logging with him. But in my slide, I also showed a GDS2, and this is what I know that David is a lot of work in that. So from GDS2 also, you can extract the reverse engineering netlist and go through that in general.
Okay.
So are those GNN models unsupervised or supervised? We are supervising them, actually. So we generate our, and this is one of the biggest or toughest tasks for us, because we had to really generate a lot of test data to train them. And this is what took us a lot of time in general. So generalization of GNNs for the unseen netlist. I think this is this question is a great question from my point of view. I would always answer this like any machine learning accuracy is as good as in an unseen data is as good as your distribution of training data set. If your actual real world data that you face during the deployment, that distribution varies significantly from your training data set, then your machine learning model will fail. And this problem in ML is called out of distribution problem. And even this variant of this problem you can face even in the domain shift problem, you know, where, for example, you have as a train for a different domain and you train it for a retrain for a different domain. But in general, out of distribution problems are very complex problem also for ML and things. So I think that the self-supervised learning based techniques is the future to go forward with that. And if you are asking me, we are working on this area now. But if you really want to start, self-supervised learning is a great area to look forward to solve all these kind of problems. And I think GNNs or any other kind of DNNs will greatly benefit from that. But again, if you ask me now, the biggest problem for that is the training. If you look at this, who are doing the self-supervised learning, the big enterprises, because for self-supervised learning, you need a huge training power. Where do we get in the regular organizations? So.
Well,
I cannot see any further questions.
I think that has answered all the questions. Right? Thanks very much again, Shafique. Excellent talk, and I think it's night time for you now. And thanks very much again. Right.
Yeah.
All right.
Thank you very much.
Yeah. Thanks. That is concluded our last talk, and thanks everyone for still sticking around a little bit. And I hope, Andrew and I hope you have enjoyed a 4-day feast of different aspects of AI machine learning for IC design and EDA, from different machine learning techniques, deep or shallow machine learning, reinforcement learning, self-supervised machine learning, whatever, right? And meanwhile, different applications from physical design to manufacturability to verification, and so on and so forth, right? So it's security, right? So, just for your info, right? So a lot of people asked whether the recording will be posted, right? Actually, 2 recordings, November 4th and 5th, have already been posted at the TILOS website, which is NSF AI National AI Institute, directed by Professor Andrew Kang, and I'm also part of that. So it's already there, and for today and yesterday's video, it will be posted once we do some cleaning. So please check them out. And it's also going to be shared with IEEE CAS, and then I do some more production kind of posting and dissemination. So last but not least, thanks to all the speakers for the great talks, and thanks to all the audience, great question and answers and interactions. And also thanks to all the students, organizers, and staff for the great help. So Andrew, do you have anything to add or?
No.
Concluding remarks.
Same messages. Thanks to everyone. As David said, it's been a great 4 days, and hope that people